opportunity for me to be back again here at the University of Southeastern Philippines. I think the last time I had a face-to-face with the examinees, I think that was in 2007 when I was still with the mining company. So the way things will go right now for the lecture is that we're going to have an introduction about stress and strain, and then we're going to focus on the main features, which I think would be the focus more of your board exam questions. That would be about the fold, the different types of the fold, and the shear sense indicators. I think these form the meat of the lecture for structural geology. Okay, so I think all of you have already taken up physics, and maybe most of you hate physics, but well, that's my PhD, geophysics. But regardless, when we talk about structural geology, in a way, we need to do some mathematics. We also need to do some physics, but we'll just focus on the very basic part, focusing about tectonic structures. Tectonic structures, as we all know, are mainly products of the movement of the plates. We know that the plates move away from each other, they move towards each other, or slide past each other. And for that reason, it is important to understand how structures are formed because of these plate movements. And in so doing, this is what we need to talk about, the force. We are familiar with the force, which is force is equal to mass times acceleration. But when we talk about the plates, we are talking about stress. The difference between the stress and the force is that the stress occurs as pair of equal and opposite forces. So if there's a component like this, there's another component on the other side because they always occur in pairs, okay? And opposite forces. So if you're gonna think about it, if we make use of, what's the red button here? Okay. So if we're gonna analyze this, right, so just how the stress is actually distributed, obviously the stress is more concentrated in this portion because the area is smaller, right? If the denominator is smaller, then you expect the stress value to be higher. So if that is how we actually look at it, we'll try to analyze, of course, not just in terms of the magnitude of the force, but as well as the area that is affected by the stress. Remember, the stress is the cause, right? It's the cause. And what will be the effect? The effect will be the product, and the product will be the fault and the folds. Okay? So if we're gonna move further, stresses may be tensional. So when you talk about tensional, by the way, guys, I talk quite fast. Now, if you're not able to catch up, please interrupt me. But I hope you are able to catch up. No? So do not be shy. And if you have questions, you'd better ask. Okay? Because, you know, geology is more of asking questions than knowing the answers. Geology is more of a model rather than a fact. Well, as far as I'm concerned. So going back to this, so stresses can be tensional, pulling apart, compressional, or shear. And for that reason, there are two types of stress. A normal stress, which is expressed as a sigma. They act perpendicular to the surface. Remember that. And that is very important when we analyze normal fault, when we analyze thrust fault, when we analyze strike slip fault, because their orientation would dictate what kind of fault would be produced. On the other hand, when you talk about the shear stress, they act parallel to the surface. So when you see the symbol tau and symbol sigma, you know what kind of a stress it is. Automatically, when you have a sigma, it always acts perpendicular. When you have a tau, you talk about the shear stress. Clear? Now, of course, stress is basically a vector. So you can, in mathematics, you can have different components, right? Depending if the stress is concentrated along the x-axis, the y-axis, or the z-axis. So that is why in structural geology, when you talk about sigma 1 is always greater than or equal to sigma 2. And sigma 2 is always greater than or equal to sigma 3. So that is the kind of relationship that you have to bear in mind. Okay? Sigma 1 is the maximum stress, and sigma 3 would be that of the least stress. And they always occur, okay? They always occur perpendicular, okay? these are three mutually perpendicular planes on which the shear stress is actually zero. We call sigma 1, sigma 2, sigma 3 as principal stress names. So as I have said, there are some components that you can actually look into. Of course, I believe that this will not be discussed further. I mean, you might not tackle this in the board examination. But remember, just in mathematics, depending on where they act on, you can divide them into different components depending on how they are oriented with respect to the plane. So as I have said, stress is the effect. Okay? Stress is the effect. So you can just imagine, okay, if principal stress are equal, meaning to say sigma 1, sigma 2, and sigma 3 are equal. You can just imagine a cube, and then we apply sigma 1, and then we apply sigma 2, and then we apply sigma 3. Okay? If they are of equal magnitude, what kind of effect would it have? Would it have an effect on the change? Would the shape change? Would the volume change? Would the area change? If I ask you that kind of question, what would happen to a piece of rock when we apply equal stresses, meaning to say hydrostatic stress or lithostatic stress? What kind of change would it accentuate? A change in shape or a change in volume? Which one? It has to be the volume. So you can, that's why if we put a rock at depth, okay, we put it below the ground, quite deep, we should expect some sort of a lithostatic stress in the sense that it acts some sort of a hydrostatic stress where the principal stresses are equal. On the other hand, when the sigma 1 and sigma 2 and sigma 3 are not equal, then you have what we call a deviatoric stress. It controls the extent of the shape change or distortion in a body. So that's why when you talk about faults, when you talk about folds, oftentimes you are talking about deviatoric stress because sigma 1, sigma 2, and sigma 3 are not equal. You can just imagine what exactly are these sigma 1, sigma 2, and sigma 3. If you're going to think about it, in a regional context, we have different plates. Each plate, they have different shapes. Each plate also has a different size. Each plate has a particular velocity. These three factors would dictate also the magnitude of the stress that they would impart onto the body. So just like the Philippines, you have the Eurasian plate on the western side, also called as the Sunda plate. On the other side, you also have the Philippine Sea plate. And the Philippine Sea plate is very, very small, right, compared to that of the Eurasian plate. If you bang them all together, it would have a different effect with respect to that of the Philippines. Okay? In the same way, when you have Pacific plate is further to the east of the Philippines, right? The plate to the east of the Philippines is not the Pacific plate, but rather it is the Philippine Sea plate. The boundary is the Manila Trench. It is the Marianas Trench. Right? So you have Guam to the east of Guam. That is the Pacific plate. So if you look at the tectonic plates of the world, Pacific plate is so big. It's moving northwestward. So, and the Philippine Sea plate is so small that because of the westward movement of the Pacific plate, it's able to push the Philippine Sea plate northwestward. And that's the reason why the Philippines is also moving northwestward slowly and counterclockwise, especially for Luzon. So eventually, obviously, Luzon, at least for that portion of the Philippines, will be part of China. So we have to be friends with China, right? So that's why if you want to really analyze what is happening, whether it's a microstructure or macrostructure, you have to look at a regional point of view. If you want to at least predict the movement of the faults, you can look at the movement of the plates and it will give you an idea, and I will teach you how. Are we clear on this? Questions? None? Okay. So stress, again, is the cause. So when we talk about the effect, that would be the strain. So when you talk about the strain, right, the end product there would basically be what we call deformation. So that is the end product of a deformation. So the nature of strain can be translation, rotation, distortion, and dilation. So when you talk about translation, the body is moved from one point to the other. Just like when you talk about Luzon or maybe other parts of the Philippines, we move it. Or sometimes there is what we call, I can hear my voice. Echo. Hello. Na-insecure ako sa boses ko. Anyway, so there's also what we call rotation. And when we change the shape, that is distortion. And when we change the volume, that is dilation. Translation, rotation, distortion, dilation. These are all the nature of strain. That's why in structural geology, right, we have what we call dynamic analysis, right, where we try to look at how things actually move. So there are various ways to analyze structural geology. If we want to know the movement, we want to know how the nature of strain, and so on and so forth. Okay? So you can also have a bulk combination of this, right? So all of this, when you talk about distortion, dilation, that is how rocks are actually deformed. Anyway, so these are just some of the details there. So if the body is shortened, just like a fold, when we fold a body, we shorten it. So in that case, it's contractual, right? Contraction is shortening. And then when there is lengthening, then you have what we call extension. When we talk about normal faults, what do you think is it? It has to be extension, obviously, right? So the body, for example, when you have a series of normal faults, in that at the middle you have a graben, the graben would not go down if the stress direction is not extensional. Okay? So of course, when we try to analyze this, why is it extending? You have to analyze it on a regional point of view. So there are two types of deformation, a continuous homogeneous or a continuous heterogeneous. And the third time would, of course, be discontinuous. If you're going to look at it, when you talk about discontinuous, there is breaking. When you talk about continuous, there's no breaking. In the continuous, it can be homogeneous in the sense that the orientation of the x and the y axis are essentially the same. They are similar in form and orientation as opposed to heterogeneous. So if we apply this in the context of foods or the type of deformation, discontinuous deformation is brittle deformation. Continuous deformation is ductile deformation. Discontinuous deformation causes faults. Continuous deformation produces folds. And when we have ductile deformation, except for sedimentary rocks, okay, it's not really sedimentary, it's sedimentary. Okay. Baka masanay ko yung sedimentary, pag umuwan tayo, baka kayo pagtawanan sa abroad. I mean, wala namang problema because we are Filipinos. It's just that what I'm trying to emphasize here is that if you go outside, the real pronunciation is sedimentary. Anyway, except for sedimentary processes, where we're talking about relatively low temperature, tectonic processes like ductile deformation involves relatively high temperature compared to that of a brittle deformation. In the brittle deformation, it happens near to the surface. When you talk about ductile deformation, it occurs relatively deep. In continental areas, the boundary is about 15 kilometers. Usually, but not necessarily. It depends on the geothermal gradient. So when you see a fold, a tectonic fold like this, right? It's a tectonic fold. You know it is ductile. So it should have happened at the deeper portions of the crust. When we talk about fault, it should have happened near to the surface of the earth at the first order of approximation. Kasi nga, sa surface, relatively malamig. So we expect it as a brittle deformation. Clear? So maybe you're asking, what happens to the fault then if it moves? Obviously, when the fault moves, it would not go all the way to the center of the earth. Tama? Otherwise, kung yung Philippine fault, dire-diretso hanggang doon sa gitna ng mundo, di hati ang mundo. Tama ba? Kaya nga kung gumalaw ang fault, the materials that you see underneath that of the fault would just move parallel to the movement of the fault. And that is the shear zone, strictly speaking, or sensu stricto. Why am I emphasizing this? Because Shear zones has been used loosely to refer to any rocks that has been broken apart. But if you're gonna look at it, shear zone actually relates to more of a ductile deformation below that of the fault. Okay, so later on, we are going to discuss that. Questions? Baka bigla tayo magtapos sa maaga nito. Tanong kayo. Okay, so here, as I have said, when you talk about continuous deformation, we're talking about folds. When you talk about discontinuous, that will be the faults. Another term for continuous be that of distributed, and for discontinuous, you refer to that as discrete. Okay, so you may be wondering, and I'm very sure you've tackled this, how do we measure the strain? Of course, we can't see the stress, but we know the magnitude of the stress based on the strain, right? So dun nga tinatawag yung strain measurement, we make use of some reference materials, example of which is a trilobite. What is so special about the trilobite? Bakit kaya ginagamit ang trilobite? Ha? Bubulong-bulong kayo, laksa mo na kabog. Estudyante, ano? No, not necessarily. Actually, cockroach mas mahaba. Cockroach, Cretaceous pa lang yan, hanggang ngayon buhay pa rin sila. Diba? Doon makikita how resilient they are. But why is it so interesting to make use this for strain measurement? It's because if you're gonna look at this, itong axis na to, I forgot the parts of the I think this is the cephalus yati, something like that. But anyway, cephalus, so something, this one here is always perpendicular to the lines that you see here. So this axis there is always perpendicular to that one. Okay, so and you see them not perpendicular anymore, it gives you the amount of stress or the strain, the angular, right? The angular shear that describes the departure of this line from its perpendicular relationship. In the same way, you can look at this and do it in the laboratory, right? This is a granite, then you can do that and apply some stress, and then eventually you would see that this lineation is formed. So this is, again, by measuring the angle, that would increase deformation. There are other types of measurement, right? So we can measure the stretch or the extension here. It's just a very simple formula for extension. All you need to do is to look at the final length and the initial length over the initial length. That would give you the amount of elongation or extension. So magnitude and so on and so forth, I will skip that one. Point ko lang here is that there are strain markers that we can actually make use of. Example, brachiopod. The brachiopod here, brachiopod, ano ba? Ang brachiopod, if you divide that into two, one portion would be the mirror image of the other. Okay? Diba? It's not really a mollusk because a mollusk, a pelecypod, hindi equal yung shell niya. So if mollusca belongs to what phylum? No, pelecypod belongs to phylum Mollusca. Correct. Paleontology. Tama? Tama ba? Phylum Mollusca, under which would be class Pelecypoda, class Cephalopoda, and class... Basta. Class Cephalopoda, Pelecypoda, nakakalimutan ka ng paleontology. But point ko lang, be careful about this. There's a very big difference between a brachiopod, the symmetry. So if it's no longer symmetrical, then you can use that as a strain marker. In some cases, they make use of the class of the conglomerates as well as the oogoids that are present in the limestone and sometimes the vesicles. But you have to be very careful about this because you can only make use of this provided that they are of similar elongation. Okay? Pag iba't iba ang shapes ng mga vesicles ninyo or even the class, they don't show a particular orientation, very unlikely that they had undergone that sort of deformation. Okay? So there are indeed fossils that you can use. So strain, you now understand the strain, you now understand the stress. Now we go to the folds. Mayroon bang tanong? Sa chat. Hello. Here's the SQ. Wala. Okay. Now we have a lot of folds in the Philippines, correct? We do have a lot of folds. When you talk about the folds, it doesn't mean that it's like that. It can be homoclinal, just like this. It's oriented in one direction. We talk about the strike and dip late tomorrow. I hope that you still know your strike and dip. So, folds are products of ductile deformation. So, pag nakakita ka ng fold, ay malamang doon yan sa ilalim. Okay? Unless nga sedimentary. Can you give me a sedimentary fold? What do you call this? What do you call that? Slump, syempre. Now, how would you know that a fold is a product of tectonics and not sedimentary processes? How? Deposit A. Teka, baka naman permanent to. A, B, C. If we deform that, it would be like this. Correct. A, B, C. Tectonics. Pwede. Ito ba ay pwedeng tectonics? A, B, C, D. Can this be a tectonic fold? Case number 2. Yes or no? Why? Assuming, of course, that this is older and that is younger. Diba? Assuming. Why? The principle of superposition is only applicable when we talk about undeformed horizontal strata. Why is this not possible? Huh? Hindi homogeneous unfolding. Well, most importantly, if this is a product of tectonic folds, this one, at least the older part should also be folded. And here, if this is young, then there has to be a angular unconformity there. Okay? So your basis here would be the older unit there. Understood? Hirap magbura. Anyway, so let's talk about folds. Okay? So as I have said a while ago, when you talk about folds, they are products they are product of brittle deformation. You look at this there, this is the fault there. And as you can see, as it goes down like this, it doesn't go all the way down, but rather its movement has resulted to the what? Deformation of the underlying layer. Walang breaking dito. They just flowed parallel to the movement of the fault. And that's the reason why they were saying that when you talk about brittle deformation, they occur on the upper part and the folding occur in the lower part. Of course, when you talk about how deep it is, it really depends, right? When I say it really depends, if it's still sedimentary rock, we don't expect that it had been below where temperature was high enough to cause metamorphism. So depende yan. Pag sedimentary, preserve pa rin yan, hindi man sobrang lalim niya. But it is still below the brittle deformation. It translates to a metamorphic rock, then things would be different. So when you look at the continental area, it's about 15 kilometers there, okay? But we are talking about island arc systems here in the Philippines. The Philippines is not continental. Palawan microcontinental block is not continental. Take note. Huh? It is not continental. It has some continental-derived sediments, pero at the same time, meron din siyang oceanic component. What made it continental is because it was derived from the eastern margin of mainland Asia, which is part of the Eurasian plate. Baka confused kayo when you talk about Palawan microcontinental block. Anyway, so when you talk about here, ductile deformation, the ductile deformation is mainly promoted by high temperature, relatively high, relative with respect to the brittle, and slow deformation rates, while low temperature and fast deformation rates lead to brittle deformation. So when you talk about folding, it occurs mainly in this part, and above that would be the brittle deformation. Okay? So you're familiar with the different types of folds. We have to know this because usually in the board exam, they ask folds, the classification of the folds. So we have to know all of this, right? So the hinge is the what? How do you define a hinge? Huh? So that's the maximum point of curvature. Is it the same as crest? Is the crest also the same as the hinge? So the hinge would be here, the crest would be there. Crest is the highest point of the fold, right? So the crest does not necessarily coincide with the hinge. So be careful about that. So other parts, of course, so the line that connects points of maximum curvature obviously is the hinge line. The actual surface is that imaginary surface that tries to divide the fold into two equal parts. Okay, and of course you are all familiar with the limb and the inflection points, which are points of zero curvature, where the sense of curvature changes from that of from convex to that of concave. So this would be the inflection point. So nagbabago na siya from convex to that of concave. So I think you're all familiar with this, but you have no choice but to memorize this, right? So we can classify the fold according to the tightness. You see how the classification changes. Gentle is about 180 to 120 degrees. Okay, so you're talking about the interlimb angle. If it's 120 to 70, that would be open. Close is about 70 to 30. Tight would be 30 to less than 5 degrees. So that would be on the basis of tightness. You measure according to the size of the interlimb angle. I guess you have already memorized this. Sige. Ako hindi ko memorize yun. Diba? Pag mag-board ako, siguro memorize ko ulit yan. So according to the orientation of the fold hinge. So this is the fold hinge. So if it's vertical, it's vertical. If it's plunging, then that's the plunging. There you measure there. That's the amount of plunging. And if it's horizontal, obviously, it's a horizontal type of fold. So in terms of the interlimb angle here, how do you classify this fold? Yes. So balik tayo. So about close. Tama. Okay? Yan. For symmetry, if the fold is able, actual plane is able to divide the fold into two equal parts, then that would be obviously symmetrical. And if not able, it's asymmetrical. In this case, is that symmetrical or asymmetrical? Not so symmetrical. Okay. Sometimes kasi nabibwisit ako sa mga ganyang tanong eh. Magbibigay sila para actually, pero if malamang sasagot nila dyan symmetrical. No? Pero if you're gonna measure it, it's actually asymmetrical. Tama. Pero kung sasagot ko dyan at the first order, I would talk to say it's more of a symmetrical type of fold. Right? So here, according to the plunge of the hinge line, so you can see this is a plunging, it's 10 to 30. If it's vertical, that's 80 to 90. It's a horizontal, 0 to 10. If you're talking about the actual plane, then it's about 0 to 10, the orientation of the actual surface. It's recumbent, gently, moderately, steeply inclined, upright to recline. As you can see, I'm not discussing this in detail because for obvious reason that this is self-explanatory. But what I would like to emphasize is the recumbent fold. The recumbent fold is one of the reasons why the rocks are overturned, right? You can just imagine this. If I will draw it, deposit A, deposit B, deposit C, okay? Then we fold it. A, B, C. Fold it again, recumbent. A, B, C, B, A. And then erode this part. This becomes the surface. This is oldest. This is youngest. This is oldest. Sorry, this has to be C. That is youngest. And that's the thing here in the Philippines, because the Philippines being an active zone, right? A lot of our rocks are actually overturned. Before you get the strike and dip, make sure that you know where is the up side and the bottom side. Diba? Alam niyo naman yung mga sedimentary structures, maybe we will run through it. If you have a piece of rock, ibigay ko sa inyo which is the top and which is the bottom. Again, very, very clear. The strike and dip, okay, would only become significant if you know where the yanging direction would be. And for that reason, when you're talking about a fold like this, symbol for fold, paano ba ang yanging direction for fold? How? How do we put the symbol for yanging direction? Hirap lang. If this is older, this is younger, okay? The Y, yung paa ng Y points to the yanging direction. There. You put this symbol. Get it? Yung paa ni Y points to the yanging direction. Okay? So if I talk about syncline, ano ba? Paano ang syncline? Oh, ganito. Ganyan. Hindi. This can also be a syncline, like this, provided that this is young and that is old. Wala namang sinasabi sa syncline or anticline na form. When you talk about the form, you're talking about either a syn form or antiform. But when there is already anticline or syncline, you are referring to the age of the rocks. If the core is the older one, that is the anticline. If the core is the younger one, that would be the syncline. Get it? Ang hirap ang bura dito. Anyway. Ay, hindi. Ako na. Nakakaya naman sa'yo. Baka utang na loob ko pa. Hindi, joke lang. Parang semi-permanent yung pen na binili nyo, ah. May ganun ba? Semi-permanent pen. So, of course, meron din tayo to. You can classify this, right? So, pag tinanong sa inyo yung classification, like that, this is an asymmetrical fold, right? You can also classify it in terms of the interleave angle. Maybe this is closed. But there is also what the term called chevron fold, where there is a strong competency contrast between the very weak and that of very hard layers. So, they normally occur like this, and there is a sudden what? Abrupt change, okay? From this point, nag-iba ka agad yung angle ng dip natin at the same time the orientation of that. So I think you're familiar with that as well. So this is an example of recumbent fold there. Very, very nice, right? Nice. Marami naman tayong ganyan eh. Ang problem sa atin, panay bulok yung outcrop natin, di ba? Bulok siya, kakabuisit. Nauubusan na nga ako ng outcrop eh. Baka before you know it, wala nang makita sa Luzon, nandun ako sa Mindanao. Okay, so this is what I am saying there. Take note of the Y there. Okay, take note of the Y. So the arrow there points the yang direction. It has nothing to do with the age. So if I ask you the question, is antiformal syncline the same as synclinal antiform? Antiformal syncline, is it the same as synclinal antiform? Hmm. Antiformal syncline and synclinal antiform. Pareho o hindi? Ito hindi. Kayo pareho? Okay. Ganito lang naman yan. Ano ba yung adjective sa synclinal antiform? Kuwari, beautiful lady. Oh, so, beautiful lady. Lady is the noun. So, gagawa muna ako ng lady. O, ganyan, no? Beautiful lady. O, lagyan ko siya sabihin ng earrings. Tapos makeup. Okay? So, if I were to draw an antiformal syncline, so adjective muna siya. Antiformal. O kaya pwede ng noun. Pero para mas madaling antiformal, gawa muna ako ng antiform. Antiform is a type of fold where the limbs move away from each other. So that is an antiform. How would it make it a syncline? So I would have to put a yang direction like this. Correct. How about synclinal antiform? Same. It's an antiform. Make it a syncline, then I will put a Y. Tama. Tama ba? Ganun lang naman yun, huwag kayo maguluhan. Kasi adjective at noun lang yun, niloloko lang kayo. Ganun lang kasimple yun. Di ba? Sa board exam lang naman, pag kayo ay kinabahan, ang gagawin ninyo? Huminga. Di ba? Ang ginagawa kaya kinakabahan yung mga tao, binabasa muna niya lahat ng mga tanong. Tapos, oh shucks, oh shit. Ano kaya? Isa lang. Pag hindi kayo segregado, lagyan niyo maliit na mark, maliit na tuldok. Di ba? Isa-isahin nyo lang siya. Pabayaan mo lang iba. Kabahan ka na suli pag lahat may tuldok. Di ba? Ibig sabihin, hindi ka sigurado na kung kakakabahan. Saka ka nakakabahan. Ganun lang naman yun. Pag kinabahan ka, stop. Yun. Kasi hanggang alas 4 naman yung exam eh. Di ba? Okay. Get it? So here, more of that. So this is what? This is an antiformal, antiform, right? I don't know if it's a syncline or anticline. I don't know because I don't know the age yet, right? So a cylindrical and non-cylindrical fold, the difference between these two is that if the stripe changes, okay, if the deep angle changes along stripe, it's non-cylindrical, just like this. Along the stripe, the deep angle changes. If it does not change, then it is a cylindrical. Okay? Diba? Boring. So other forms, if it's three-dimension, again, antiform, synform, a dome, a basic, a whaleback, a canoe, a saddle, a shore. Okay? So a periclinal type of fold, just like this, is a totally plunging. It's plunging this way, it's plunging that way, this plunges that way, it plunges on the other side as well. And all of these are types of non-cylindrical fold. Now, why is it that when you look at this, right, there is a harmonic folding, and this is a disharmonic folding. Why do we have that kind of folds? Why? When you have disharmonic, what does it imply? Huh? It was once deposited horizontally, so it's disharmonic. Same type of rocks kapag? Pwede. Biglang natawa. Tama naman. Tama ka naman. You know why? Because rocks have different competency. When you have a shale and a sand, Sand is more competent compared to the shale. So when we fold them, there's that tendency that the shale would have shorter wavelength compared to that of the sandstone. However, it is not that's just that the competency. It's also about the thickness. Okay? So kapag makapal yung sand, for example, with respect to that of the shale, yung shale, mas magiging siyang mas maliikli yung wavelength niya. Okay? So pag meron kang interbedded sandstone and mudstone of almost equal thickness, you would notice, for example, in turbidite systems, if you go to Masara district, there are a lot of interbedded sandstone, mudstone. They just have the same wavelength. It's more of disharmonic. Oftentimes, I mean, it's more of harmonic. No, oftentimes disharmonic, there are what? There are variations in the competence of the rock because it's a reflection of the type of rocks as well as the thickness. The thicker the unit is, the bigger the wavelength. The thinner the rock is, the shorter the wavelength. Okay? So you look at this example, you see how thin they are. You can see wavelength, maikli. Medyo tight ang folding niya. So when you talk about the layered thickness, I've talked about this already. You can have a parallel fold or a similar fold. Parallel fold is that the true thickness is constant all throughout, and a similar fold is perpendicular. The perpendicular thickness is of similar length, or of similar length. And finally, please look into this, the Ramsey classification scheme for folds. Have you discussed this in your class? You've discussed this, right? Yes or no? Okay? So please take note of that as well. Diba? So you look at the deep ice guns, they actually converge when you're talking about 1A or 1B, like that. So anyway, these are just self-explanatory. No? So in terms of bending mechanism, buckling is commonly the main cause of tectonic folds there, right? So this buckling, we apply stress and then you buckle it. So it's a passive bending, it's just reacting, it's responding to the change of rocks around it. Example, this one. Normal fault caused this to bend, and that would actually cause passive bending. And that would be a passive folding as well. Okay, so if we have a mechanics of bending, you would see how the thickness has influenced the thickness or the wavelength. So thickness, shorter, thinner, smaller wavelength, and this would be thicker there. Now, in a fold, are we talking about pure extensional to pure contraction? Can we have extension in a fold? Can we have extension on the fold? It is, it's possible. Actually, look at this. And just imagine you draw a circle there. Circle. Ilagay natin sa loob. And if we're going to look at the center, here, you will see that there is contraction in the inner part. In the outer part, there is an extension. Okay? So that's the reason why when you look at some big folds, extension would produce here what? Normal faults. In the inner part, it can produce thrust faults because thrust faults are product of compression and normal faults are products of extension. And that this seismic data supports this mechanism that folding can also entail not just contraction but as well as extension. Clear? Okay. So can we just have a 5-minute break? Ha? Ano yan? Durian coffee yan. Durian coffee ba? Sige, salamat Sabi, tataba ako sa inyo. Salamat. Mhm. Elementary, sedimentary. Ah, good. Ah, okay. Ah, ano to? Para mas gusto ko to. Hindi. Kakain ko lang eh. Baka tumaba ako niyan. Laki-laki na ng tiyan ko. Ano, okay lang na lumaki tiyan ko. Ganun ba yun? Wow, dami naman ito. Ah, naya ako eh. Grabe. Grabe naman yan. Ikaw pa mag-o-open. Para kasira. Ha? Okay. Handa na ba kayo? Pwede man kumain habang nag-ano, di ba? Matanda na ako ah. Hindi ako mapagod. Okay, so let's continue. So the more interesting part for me is actually the fault. And we do have a lot of faults in the Philippines. The fault is basically we have the Philippine fault because it allows the accommodation of the stress. One way that stresses are accommodated because of the convergence of the plates surrounding the Philippines is not just in terms of the fault, but also the Philippine fault. And the Philippine fault is left lateral, correct? If it's left lateral because why? Luzon, for example, if this is the Philippines as a whole, Eurasian or Sunda plate is like this. Philippine Sea plate is like that. It's moving northwestward because it's being pushed by the Pacific plate, which is like this. To accommodate the stress, that's why it's left lateral. Right? Kaya siya left lateral. So that is the mechanism for the Philippine Sea, for the Philippine fault there. And if you're going to look at the literature, it says it's co-eval to the formation of that Philippine trench. Because of the approach is oblique, you know that you can, what what do you call this? This component of your vector component allows subduction to happen. And this now would result to the formation of the Philippine fault. This would result to the formation of the Philippine trench under what we call a shear partitioning coefficient. Okay? And the age of the Philippine fault is what? Huh? Pliocene. Diba? Ang sabi ni Aurelio at saka yung kanyang advisor si Parrier, it started somewhere in the middle of the, I think it's in the middle of somewhere in Bicol, and then it translated southward and then northward there. And you know that the Philippine fault is at least 1,200 kilometers, right? So when you talk about faults, their movement can be represented in terms of a focal mechanism solutions. If you are going to look at the map of the Philippine Institute of Volcanology and Seismology, the tectonic map of the Philippines, the movement of the trench and the movement of the fault is represented by this. This is a focal mechanism solution. The shaded part represents area of compression. The unshaded part represents area of extension or dilation. That's why when you talk about normal fault, the focal mechanism is like this. Because of extension, it allows dilation at the middle part, just like a graben. In the same way, when you're talking about a reverse, since it is compression, you expect the stress to be concentrated at the middle. So that's why you have this kind of symbol, and that would be for strike slip fault. Okay, so in convergent margins, Manila Trench, the Philippine Trench, the Negros Trench, the Sulu Trench, these are areas of convergence, and that's why it is compressional. It's often represented by this one. For the Philippine fault, it's usually represented in terms of a strike slip. Although take note, the Philippine fault has both a thrust and normal component for reasons that I am going to tell you later. Are we clear on this? Again, parts of the fault, of course, we look into what? The throat. Throat represents the vertical displacement. And if we're gonna draw this more simpler, like this, like that, this is the throat, this is the heave, and that would be the net slip. So the heave there represents the horizontal displacement between the hanging wall and that of the foot wall. Please do not be confused about the foot wall. The foot wall is always below the fault plane, and the hanging wall is always above the fault plane there. So if you see a tectonic map, by just looking at this, you should be able to decipher what kind of a movement is it. Okay? Now, in terms of the components, right? So where there are lozenge-shaped rock bodies oriented parallel to the main fault like this, that's the main core where there are a lot of deformation happening. Okay, so this would be basically the actual fault core there. Well, in terms of the damage zone, that is that volume of brittle deformed rock surrounding the fault core. And also, in that case, we're looking at the whole damage zone. So this would represent the whole damage zone, and this would be the undeformed part. Okay? So that's why when we see this in an outcrop, we usually refer to this as a shear zone. But to tell you frankly, this already involves brittle deformation, and therefore it should not be referred to as is. But anyway, there's no problem with that for as long as we can understand, we understand each other there. Okay, so are we clear on that as well? So obviously this represents a normal fault. So this is an example in an outcrop here. So this would here represent the fault core here. See this one, okay? And the damage zone is just this portion over here there. So a fault line, intersection of fault with the surface. So here is the San Andreas fault. It has a very different mechanism when you talk about the Philippine fault, right? So it's very, very different. So when you talk about the fault zone, in a fault zone, the Philippine fault zone is how many kilometers wide? How many? Ano, 1,000? Of course not. Width. Grabe, 1,000 width. 1,000 kilometers, grabe, lampas-lampas na. Width. When you talk about a fault zone. Okay. Okay, top view. Well, gawin natin ito, okay? So this is a fault zone there. So if we're gonna draw this, maybe in a 3D, something like this, okay? Like this, okay? So this is the fault zone. Get it? So you can have overlapping faults like this. The whole thing represents a fault zone. So sometimes there's this tendency that the fault to actually branch out as it gets near to the surface. Why? At the surface, for big faults, they have the tendency to branch out like this, several segments. But if you trace them, they have the tendency to join. So my question is, why is there a greater tendency for faults to branch out near to the surface or on the surface? Why? Because, ha? Hindi, brittle naman lahat ng fault eh. Di ba sabi ko fault ay brittle. Pag nabasag ang ulo mo, brittle yun. Pag sinuntok na deform, uy, ductile. May oras, interpret. Bakit kaya? Because on the near to the surface, the confining pressure is less. So mas madali siya mag-branch out. Sa ilalim, siyempre, mas mataas ang pressure, mas mahirapan siya mag-branch out. You would notice that in mining areas, in operating mines. Sa operating mines, pag nasa taas ka, ang dami yung veins natin, di ba? Pag yung fault, pwedeng lagyan ng hydrothermal fluids, it becomes veins. Pagdating mo sa ilalim, nag-merge siya. Get it? And the whole thing is actually a fault zone. And the width of the Philippine fault zone is about 5 kilometers. Not 1,000 kilometers, di ba? Grabe. 1,000. From Luzon to Mindanao, ganun ka. Taba. So here, you could see that the fault line is over here, and the fault zone, if there are some overlapping faults, that would be the fault zone. So other classifications are parallel faults. Strike and depot faults are essentially the same, just like this. Or an Enchelan faults, relatively short faults that overlap each other, just like that. Peripheral faults, circuit or arcuate faults that bound the circular area. Or radial faults belong to a system of faults that radiate out from a point, just like this. And echelon faults are quite important because they are responsible in part for having a thrust component or a normal component. You can have a left stepping fault or a right stepping fault. If I give you this top view like that or like this, okay? In this case, is this left stepping or right stepping fault? This is what? Right stepping, going down. Okay? So if this is a left lateral fault, hirap mag-erase lang dito. Ano bang klaseng semi-permanent? Sa susunod yung ano, semi-permanent. Wawa ka naman dyan. Ah, yeah. So this is an example of sinistral or left lateral right stepping fault. Okay? Get it? So a right stepping left lateral fault would have a what? A normal component or a normal component or a thrust component. Normal or thrust? Sabi niya normal or thrust. Sige, mamaya tingnan natin kung sinong tama. Okay? So there are other classifications of a fault. You have a strike fault. Strike is essentially parallel to the strike of adjacent bed. A bedding fault, strike fault that is parallel to the bedding. A deep fault, strike parallel to the deep of the adjacent bed, and so on and so forth. Now, let me also emphasize on the presence of an echelon faults. You have to do, in terms of engineering, this is important. Okay? If your house is here or if the structure is there, the Philippine Institute of Volcanology says that there is a no-build zone if you are within 5 meters from the fault. Tama? Okay. Medyo kabado ka ron. Because when you're talking about the Philippine fault, ang sinasabi actually ng FIVOL is 5 meters from the deformation zone, active deformation zone. So if you have a branching fault like this, dapat magtatayo ka malayo doon there. Because this is the deformation zone. Doon tayo nagkakaproblema. I give an example. SM somewhere, I'm not going to mention the location. Okay? Nagukay sila rito, nag-borehole sila dyan. In fact, nagkaroon sila ng pit dito. So nag-aaway-away na. Wala sila nakitang fault. Malamang nandito ka. Pero ang hindi nila alam, that Marikina fault is a branching fault there. Okay? So be careful dyan, di ba? Kahit wala dyan, ay nandun pala, you are bounded. Dapat no build zone yan. Supposedly. So please look into this. I'm not gonna, kasi these are all self-explanatory. These are just a classification of the fault on the basis of the attitude of the fault. Okay? So if it's a low angle fault, it's less than 45 degrees. High angle fault is deep more than 45 degrees. So what are the evidence of faulting? One is the fault drag. If you're gonna look at this, right? You look at the layer there, na drag. Ama. This na drag. It was dragged because this moved down. The other side moved down. Tama ba? Clear? This one? So the fault drag is very important. That is one evidence of faulting. Okay. There are some features that are very obvious there. If I'm gonna look at it again, this portion over here, there, it was dragged up because of this movement over there. So that is one evidence of faulting. Another one is Riddell shears. Riddell shears can be seen on an outcrop, okay, outcrop scale, or maybe also in a regional scale. Now, if we're going to look at this outcrop, this is unfractured, relatively unfractured. And then at the middle of the outcrop, they are very, very fractured. Deformation can actually be confusing sometimes. But you can see that the kind of deformation that it has, look at this, it's very fractured as opposed to that. That can also be an evidence of faulting. So I think you have already studied the Riddell shears, right? So the R prime is antithetic to the main movement. R is synthetic, and we have also the pier shear. So the R shear there represents where the movement is. Example, this one, it's a low angle. Look at the angle of the R shear with respect to the main trace of the fault. It's about 30 degrees or even less than that. Okay? You get that? And that is the synthetic shear though. So the movement there is actually right lateral. Correct. So it can be a regional scale. For example, this is a regional, a very big area. So in remote sensing, you can actually try to trace that one. That can also give you the trace of the fault. So all of these are arranged in echelon. Another thing is the conjugate fault. These are a set of faults at an angle of approximately 30 degrees to the sigma 1. Okay? So in normal fault, sigma 1 is oriented vertically. So in that case, these are all conjugate to each other, right? So that is another evidence of faulting. So there is also an echelon veins. If you want to know to determine these veins over here, obviously, we form first the fracture, then we infill this with secondary minerals, for example, quartz, and then we apply faulting, and this would be the orientation there. You call that as an echelon veins. It's very easy. It's very common to see this in the Philippines, where we have a lot of hydrothermal. So pag nakakita kayo dyan, alam niyo na yung magiging sense of movement. In the past exams, they showed just photos and you will be asked what would be the sense of movement. Okay, so try to analyze this. You can also have what we call a dilational job. First, this is the movement, so there is a bending of the fault, right? So that's the bending of the fault, and eventually here, there's a rupturing. And in the presence of rupturing, then there comes now the infilling of that of the veins. Okay? So that would be again a dilational job. This moves that way, that moves that way. Basically, that would form an extension here. Kaya mataba siya dito. Kita nyo? This is extension like that. Example, it's just like a bending of the fault, like this. If the fault bends this way, like that, right lateral, so this vector goes this way, that vector goes this way, there will be extension, so some form of a normal fault, extension there, opening, so you have a big opening there. Get it? So of course, this is most common to us, offset marker, right? Very easy, but take note, okay? This is only at one dimension. In describing an outcrop, you have to, as much as possible, go around. Okay? Bakit? Sample. If this is a right lateral fault, symbol in a cross-section, so dito yung cross-section, paano ang symbol? X. Right lateral, tama. So this would be X. That. Tama. Tama. Bakit? Arrow. Correct. So what I'm saying is that if you're going to look at this, right? Ang makikita mo lang, there's no offset. It's just a fracture. So you're just looking at one dimension. So that's why if you're not sure of the movement, you use the word apparent. Pag nandito ka, mas obvious. Correct? Especially if there are permanent surface structures there. What else? So what kind of a fault is this? Normal, reverse, or strike slip? So that's it's normal fault. Apparent movement. Okay, apparent. So here, another evidence of a fault is what? The offset ridge. You look at that, makikita yung pag-offset ng ridge mo. So this is an example of the Philippine fault, the Vegan-Algo fault, which is a branch of the Philippine fault there. It consists of several branches there, and there are offset spurs and offset streams. So you look at the ridge, if they're consistently offset like this, something offset like that, you know that there is actually a fault. So that's why in Google Earth is very useful, kahit hindi ganun kaganda yung resolution. When you suspect a fault, you ridge and the river, you trace it. Okay? You trace it. If there's a consistency in the bending of the ridge or bending of the streams, obviously that is a fault there. Okay? So, ito yung ginagawa. Like this, left natin, you look at this. Okay? Hindi masyadong halata dito, but you know, you look at this portion over here. Hindi ba kayo nagtataka? Hindi. Ano ba yung tsura ng bundok? Peram nito Hirap eh. Peram nito Nung tayo ay bata, nung bata pa tayo, grade 1, grade 2, mag-drawing tayo ng bundok, ganyan lang. Tama? Teacher, ganyan lang yung bundok. Lalagyan ng araw, tama. So you have already that concept of a scarp. Pero ang bundok is actually like this. Correct. So pag nakat to ng fault, ng strike slip fault, itong ridge na to, Rama, tayo ka, anong pangalan mo? Ano? Rafael. Tayo ka, para may silbi ka. Samayan mo. Pwede. Yan. Yeah. Makakatawa talaga to. Daling ko siya rito because of strike slip. Tama. Nakagaganito siya. Hawakan mo ganyan Okay. So yung ilog, syempre dati dito dumadaan. Kung lalagay ko siya dito, ang ilog dito dadaan. Pag in-offset kong ganyan, the ilog dadaan dito, gaganito, ganun. You call this now ridge as a shutter ridge because it blocks it. It fronts a particular valley. Okay? Just like this, shutter, S-H-U-T-T-E-R. Sorry for those doing virtual. Ang hirap kasi. So just like this that you see here, okay? This is a geomorphological anomaly. All the ridges are oriented this way, and then suddenly there's a ridge there. Naka-block siya. Okay? So that is a geomorphological anomaly. So in geomorphology, what you do, you also try to trace the ridge. If there is a consistency in the way they bend, then again, that can be an indication of the movement of the fault. Okay? And of course, just like the river, look at this. This river bends this way. This river bends this way. There is a subtle bending this way. Tama? There. Ito, pagdating dito, medyo subtle lang siya pa ganyan. So, consistently pa ganun ang bending niya. Okay? There. Get it? So, because of that, most likely, there is a fault like this. What kind of movement is it? Left lateral or right lateral? So it is right lateral. Right? So same thing here. There can be, because of faulting, it can cause, obviously, the fracturing of the rocks. So fracturing, that is where the groundwater would pass through. Diba? Springs are nice because they're source of water. But springs also connote that there are fractures. Di ba? Kaya pag nagkakaroon tayo ng bundok na dating walang spring sa anan, tapos biglang nagkaroon ng spring dun sa ibabaw, dun sa labas, alam mo, may fracture. Yung taas ng bundok. Gets ninyo? Hindi. Parang landslide lang yan. Indication ng landslide, di ba? Kung dati, walang lumalabas na tubig sa paanan ng bundok, tapos after a few months, biglang may lumalabas na tubig, alam mo yung fracture doon sa ibabaw. Ganun din dito when you talk about this. But mechanism is that if there's faulting there, that would cause a lot of fracturing, and that is where water would be able to go out there. So escarpment is very common for us, and we've seen a lot of escarpment. This is just a small escarpment there. So this is an escarpment. You can trace that, and this is also a series of escarpment. You know that there is a fault because one is that the base of the mountain is very linear. Number two, there's a sudden change in topography. Number three, the distribution of landslides coincide with the scarp. Remember, if the landslides are continuous and they seem to define in one line, that can also indicate the presence of that of a fault. So in the case, this is also a fault there in Taiwan, which is a thrust fault. In Taiwan, the thrust there is the on-land expression of the Manila Trench. Manila Trench is a trench. in the Philippines. But if you go to Taiwan, it becomes a thrust fault. Why is that so? Because the western side of, just like in the Philippines where we have a Palawan microcontinental block, there was also sa so-called continental derived na bumangga sa other part of Taiwan. So pag siya ay continental origin, what is the characteristic of continental with respect to oceanic? What? When I have a continent and then when I have a sea floor, okay, which will subduct? The sea floor, the oceanic plate, or the continental plate? And why? A oceanic plate would subduct for the simple reason because dense, because ha? Ano yung composition ng ano? Pero magnesium, so basically an ophiolite, di ba? Di ba? Mataas ang iron niya, mataas ang magnesium. Pag maitim yung bato na igneous, malamang mataas ang iron and magnesium. So mabigat. Bakit mabigat? Because iron and magnesium, they have high atomic weight. Tama. Kaya pag titingnan mo yung atomic weight niya, titingnan mo sa chemical equation para maano yung table of elements ninyo. Tingnan niyo lang siya, ay mabigat to, mataas. Malamang dense siya. 'Di ba? So pag maitim siya, ay nako, mabigat to. Ba't ka tumatawa? Hindi, I'm talking about tao, hindi sa tao, ano ka ba? Ang continental, silica, lighter. Correct. Tama. So in the same way, continents are what? They are old and they are thick. So since they're lighter, they're thick, it's so difficult for it to subduct. So that's why when eastern part of Taiwan and the western part of Taiwan collided, okay, there used to be a trench there. Nung bumangga sila, wala na si trench. Okay? So if you trace the Manila Trench, if you want to see the Manila Trench, you go to Taiwan. So what else do we have? Well, sand pans, you are all familiar with that. Of course, depressions can also form there. And repetition and emission of strata can also be an important marker, can be an important marker. Example, I made a borehole, A, B, C, okay, D. Okay? Sabihin natin ganyan ang borehole natin. Normal or thrust? Nagtrabaho ko sa isang geotechnical company. Normal or thrust? The same way, if I have A, B, D, E. Normal or thrust? O hindi niyo alam? Sige. Nabibwisit ko sa... Gusto ko lagyan ng alcohol to eh, no? Okay ka pa dyan? Kawawa ka ng tagahawak. Ano ba rule mo sa buhay? Kung ako may insulto ako, miss ka dyan, akong bahala. Magbumaksak, eh di bumaksak. Depende. A, B, C, D. So let's talk about reverse fault like this. So this became C, B, A. So let's say this is O. Okay? If we made a borehole like this, so a vertical borehole like that, and then we log it. First, we encounter A here, then B, then B, then C. Repetition of bed, thrust fault. Okay? The same way, this is a normal fault, okay? Say this would be E, D, C, B. And then I made a borehole. Teka, parang bobo ko. D, C, B. Tama, di ba? Encounter ko, what? A and B, bahala na siya kung sino tamaan niya. B. Then pagdating dito, D. There's an omission of strata. Right? So it's a normal fault. Tama. But be careful. The borehole or the borehole that you see should show some indications of faulting. Ngari, basag-basag yung bato. Number two, you see slickened sides. Okay? Because omission of strata can be also a product of unconformity. Deposit A, deposit B, deposit C. At time 4, erode C. At time 5, deposit D. A, B, D, there is also an omission of strata. Okay? So you have to look for other evidence as well. But at the first order of approximation, in the absence of any geological information, if we're just talking about the omission of strata, then in terms of the fault, it's likely a normal fault. Clear? So you are all familiar with unconformity. And an unconformity is a buried erosional surface, right? Buried surface representing erosion and or non-deposition. So slickened sides is also another features characteristic of fault movement. So alam natin yung movement. And a cross-section like this, kung magaspang, kapakapain mo si fault. Kapakapa, alam na kung ano yun, no? So movement dito is like this. So this block got removed. You get rid of that block. Ito yung outcrop, that's the outcrop. So the movement is this, like that. Get it? So look at this. Kapakapa, kinapakapa. So if you're gonna look at this portion here, ang step niya pababa, like that. So you remove this block kasi na-erode na. You expose this. So the movement, itong batong to mismo, move up. This, the one that was removed, move down. Get it? Uy. Okay. Questions about that? So I already gave you different, different criteria for faulting, but there's another one that's very obvious in the Philippines that we have not discussed. Can you give me another indication of faulting? What? Fault gouge, yeah, sige. Or break siya, fault break siya. Durug-durug yung bato, which already was represented in the fault core that I showed you. What else? There's one very important feature in the Philippines that tells you where the fault is. Trench parallel. Di naman ko nakikita yun. Alam niyo what? You look at the distribution of mineralization. If the distribution of mining companies, they tend to parallel the fault subsidiary to the Philippine fault. Not the Philippine itself, but subsidiary or secondary to the Philippine fault. Nandun siya. Diba? Because you know that faults are produces fractures for hydrothermal fluids to go up and then cause mineralization. Okay? Tama. So, importante yan. But of course, nag-study naman na kayo niyan eh. Tingnan ninyo. So for the normal fault, you are all familiar with the sigma. If you're going to look at the normal fault there, sigma 1 is oriented vertically and sigma 3 is oriented horizontally. Why? Why is it that the normal fault, sigma 3 is oriented horizontally? Why? Huh? So it's easy to actually extend these blocks over here if it meets least resistance. So sigma 3, mahina siya, di ba? Siya ang pinakamahina. and therefore it's oriented horizontally, and this sigma 1 is vertically. So normal stress, as you have mentioned, represents an area of extension. So we have discussed this hanging wall block, the footwall block, and the cutoff line. The cutoff line is that line there where the stratigraphic horizon or the geologic horizon, in this case here, meets the fault plane. So this is the fault plane, that is the cutoff line for the footwall, and this would be that of the hanging wall. Okay. So in terms of what we call this, piercing points is a special kind of cutoff that refer to the displacement of a specific object. For example, that of a road, right? That can be traced from the footwall going down to that of the hanging wall. So that would be the piercing point. So there are basic geometries for normal fault. Some are planar like this. Sometimes they occur as dominoes like that, and some are district. Okay, what conditions promote district faults? What conditions? Why is it that some faults are planar and some normal faults are district? Why? When you see that kind of morphology, what does it connote? Huh? District faults happens whenever it meets a relatively thick incompetent layer. Example, if this is a sand, and then this is a thick layer of shale. So this is a thick layer of shale. If there's a normal fault, it will be like this for sand, okay? Like this. If it meets an incompetent layer, just like a shale, it would now refract like this. You got that? The presence of district faults connotes the varying competence of the rock. Okay? But of course, if you have interbedded sandstone and mudstone, it tends to have a planar one. But if you have a thick incompetent layer, then you can produce a district fault. And a product of a district fault would be a rollover anticline, just like what this one. Okay? So this is an example of a planar fault. This is part of my PhD thesis in Dingalan. There are a series of normal faults. Look at the beds like this. They are oriented like this. They are oriented this way because of the presence of this series of planar faults. You call this as a deep slope like this, right? Because the dip is parallel to the slope orientation there. So this is a very, very nice. Some point this Philippine fault in the well, before the Philippine fault extension happened in that area. Okay. So this is an example of a district fault again. You look at this seismic data, that is a district fault. This is also a planar, and this is a planar fault. This is a district fault like that. So there are other terms that you can make use. Megamullions, a district fault surface have irregular strongly curved corrugations like this. If there are a series of district fault, you call this as an imbricate system. Just like in a thrust fault, you can also have an imbricate system. Okay, and this is quite common, especially in deltaic areas, deltas. So in such case, when you have this imbricate system, growth faulting can happen. So this is an example of a growth strata. Why is it a growth strata? Because the growth strata, remember, normal faults create a more accommodation space. That's how deltas are able to prograde. One way that deltas are able to prograde out. So this is a delta like this, okay? So let's say delta. This is a slope like this. Then reverse, drain a lot of sediments. Remember, a shelf can only produce, or it can only support a particular weight of sediments. So eventually this would slump like this. Slumping would now create a district fault. And the good thing about district fault is that it creates additional accommodation space for sediments to be accommodated. And so this would be able to deposit there like that more. And then they would slump like this. So the more sediments now would be deposited there. So the delta is able to prograde out. So it's very common to see deltas having a series of listric faults or planar faults that actually prograde out into the offshore area. Okay, just like this. And you know that this kind of fault is a syndepositional. Syndepositional because as faults form, the sedimentation continues all along. Okay, so I will already explain, of course, the domino faulting. And you have also what we call a detachment fault. So this is the layer of detachment, right? So that's the layer of detachment. So these are the same fault there, and some of them can also be antithetic fault. So for fault hierarchy, if you're gonna go back here, this would turn out to be more of the master fault because it dictates the main direction of the dip. So just like this, okay? So this would be a master fault moving like this. The smaller faults that are parallel to the master fault, we call that as synthetic, and the rest, we call that as antithetic. So where do we find normal faults? In spreading centers, because these are areas of extension, correct? So you can see that there are a series of normal faults that can be produced just like this. Okay? Remember that in a spreading center, it's always a volcano, right? These are spreading centers like this. Okay? It's like that. Correct. It's like this. This is one volcano, another volcano, third volcano. Each has its own magma chamber. Kaya most of volcanoes are found sa sea. Kaya maalat yung dagat. Tama. Maalat yung dagat, di ba? That's the reason why seawater is salty because of volcanism there. And they are cut by a series of transform fault boundaries. And in that case, because this is an area of extension, then normal faults are associated with these transform faults. Okay? So where else can we find divergent boundaries? So we can have completed reefs, aborted reefs, intraplate reefs. Can you give me an example of an intraplate reef in the Philippines? Question, to which plate does the Philippines, except for Palawan, belong to? To which plate? Patay tayo nito. To which plate, based on the present setting, does the Philippines, except for the Palawan region, belong to? Kayo dyan, sa likod. Meron pa ba sa likod? Anong pangalan mo na kay Tim? Since ikaw ay tumungo doon, yes. Okay, ano sagot mo? Eurasian plate, Sunda plate, or Philippine Sea plate? Ha? Siyempre, layo ng Pacific. Nandun pa yung Pacific. Sige, mag-Bisaya ka pa. Magkaintindihan tayo. Kakainis ka naman. Si Ilocano yung kanya kamutin. Apay kayong kasta. Taga-Bagyo ako nga ruden. Sige. Ikaw naman, loloko mo naman ako eh. Ano? Hindi. Ha? Siyempre, Philippine Mobile Bell. How do we distinguish a plate? There are two important margins, a convergent margin, which is a trench, and a spreading center, which is a divergent margin. For Luzon, right? Luzon and then portion of Visayas and Mindanao, we are bounded by the trenches. So the Philippines basically is a microplate. That is the Philippine Mobile Belt. But as you go in the northern part of Luzon, right? Eastern part of Luzon, you have the East Luzon Trough, correct? The East Luzon Trough is an incipient subduction zone. When I say incipient, nagsisimula pa lang siya o nabuhay lang siya. So if you trace the East Luzon Trough, pagdating mo doon, nawawala siya. So that part, Batanes, papunta sa ganun, naka-couple siya sa Philippine Sea Plate. Kasi hindi pa nakadetach. When I say couple, nakadikit pa rin siya. But if you go to Northern Sierra Madre, that's already decoupled. Now, going back to my question, Give me an example where spreading, intraplate, aborted spreading happened in the Philippines. Where? In the same way, if you're going to look at Palawan, offshore of Palawan, west of Palawan, you would see that that margin, they are cut by a series of normal fault because at some point, Palawan used to be attached to mainland Asia and spreading that caused the formation of the South China Sea, which we refer to as the West Philippine Sea, that's spreading, right? Some point, and you're going to look at the seismic profile, you would see a series of kind of set. So you know that spreading happened. Clearly. So in Iceland, look at Iceland, right? So this is the Mid-Atlantic Ridge. These are a series of transfer fault boundaries. In Iceland, it's at the middle of the Mid-Atlantic Ridge. That's why Iceland is spreading. If you want to see the on-land expression of that spreading, you go to Iceland. This is one plate. This is another plate. This is now the boundary. Okay? So in Africa, you would also see that intraplate rifting there. This is a 3-point junction. The eastern part of Africa is spreading, right? Red Sea, Gulf of Eden, and this is now spreading dito sa Kenya. Nahahati na siya. Okay? So that's why the Red Sea, also in Dead Sea, they're called as Dead Sea. Bakit kaya? Bakit kaya? Dead Sea. Why? Bakit hypersaline? Ha? Walang precipitate? Hindi. Bakit kaya sobrang salty yan? Dahil, syempre, sa gitna niya spreading center eh. So in terms of area, nagsisimula ka na sa concentrated. Tumalon ka dyan, lulutang ka. Ba't naman ako tatalon dyan? Okay? So I already explained about delta propagation. Look what's happening to the delta. There are also a series of normal faults there. Okay? So other point, convergent boundaries. How is that possible? How is it possible to have normal faults in convergent boundaries? So this is very important, especially in continental areas. When you have India and Eurasia, what happens? Subduction is difficult because you're talking about two continental areas. They're both thick. That's why you have Himalayas. In the Himalayas, it resulted to the crumpling of the crust. Crumpling of the crust would form big mountains. Big mountains would form gravitational instability that would cause slumping in a form of normal faults. So if this is subduction, or, well, the point of collision, Himalayas would be over here, and then the slumping, the normal faults would be on the other side. Okay, so you can also form normal faults in a convergent boundary. And other than that, so this is what I'm saying, this is the collision of India, this is Eurasia. What is the India-Eurasia collision? It happened during what period? 55 million years. EUC, di ba? So nakikita mo normal faults is on the other side, behind that of the Himalayas. Clear? Okay? Now we go to the thrust and reverse fault. Now, by the way, for thrust and reverse fault, what is the orientation of sigma 1? Sigma 1 is horizontal. Bakit horizontal? And bakit vertical ang sigma 3? Because Hanging wall, it's easy to move up if it meets least resistance on this side. Correct. That's why sigma 3 is oriented vertically and sigma 1 is oriented horizontally. You get it? Okay? So that is their orientation. So the sense of shear on the thrust implies horizontal contraction parallel to sigma 1 and vertical extension there. So what are the general features? There are a series of flats and ramps. Okay? So these flats is where the thrust sheet slides along a relatively weak bedding plane called the décoma plane. This is not décollement. This is a French word. It's décoma. And then ramp, right? Which is what? We talk about ramp then. So the ramp where the thrust cuts upward through the stratigraphic sequence at an angle typically around 30 degrees Celsius, 30 degrees Celsius, 30 degrees. So where is the décoma surface? So the décoma surface is this one. This is a décoma surface. There, that is the décoma surface. This is the flat. This is the ramp. So if we want to reconstruct this, all we need to do is to bring that, pull that back here so that the orange would be what? Dito siya. Dito siya mag-join, right? And normally, the décoma surface happens in the contact between a competent and incompetent layer, usually, but not necessarily. So you can have a series of ramping there, right? So you have one, this is two, and you call this therefore, and when you have a series, like a domino effect, you have what we call a piggyback structure. So that's a piggyback structure. So this is an older thrust. This is a younger thrust. So this is the ramp, that is the flat, the whole thing here, this line is the décoma surface. So just like this is an imbricate system, time 1. Then you have time 2 there. So what's happening here is you have a fault propagating fold there. And here you call the whole thing as the imbricate zone or the Chopin structure, just like in a normal fault. So if they are bounded by the original surface, so you can see this is the imbricate zone, and now these are the imbricate zone, and now they are bounded by the original thrust package. You call the whole thing, in that case, you call the whole thing as basically the duplex. So each of these, you call that a horse. This is a horse, that is a horse, that's another horse. The whole thing is basically a duplex. Are we clear on that? Kumbaga, ito, kabayo, kabayo, kabayo. Diba? Bakit nga ba horse? Anyway. Okay, so this is an example of a duplex, right? So this one, this is the original package. It's correlative with this one over here. Okay? Kapagod. Yeah, tapusin mo na to. Break muna tayo, Pagod na ba kayo? Parang nabobor na kayo sa akin. Alam niyo na to eh. Yan, yung magbibigyan ng tanong bukas. So, the package that was transported is the allochthon. When you say allochthonous, it means to be transported. Autochthon in place. So, if we're gonna go back to this is the autochthon. These are the allochthon because they were transported. Okay? So, here, this is the autochthon. The allochthon. What remains of the allochthon, you call that as the clip. Okay? If then we erode it, expose the autochthon, then you have a window. So this is a clip over here, there. The thrust is somewhere there, and this is the autochthon. So what do we expect over here? That the older unit is on top of the younger unit there. Right? Because this light, the gray over here corresponds to this. So this is the oldest. Over there, that's the youngest. So obviously, there is a repetition of the sequence. Clear? So what are the other features that are associated with that? We have a fault bend folds. We have a detachment fold. We have a fault propagating fold. When you talk about the fault bend fold, folding, okay, they move from flat to lump. In other words, the fold already starts as it goes this part. Dito nagsisimula yung bending niya dito. Okay? Pero sa fault propagating, nandun siya nagsisimula sa taas. You get it? Parang if I have Ako nga. Ganun. Galit. Diba? Pag you form the fold like that, fold na siya. Bend. Pero yung propagating tip, pag taas din, dun siya magpro-propagate. Okay? Thank you. And then, of course, detachment folds there. Folding of a layer due to shortening above a detachment or a decoma, just like this one, right? Starting, it's starting to detach like that. So this is an example of this is the autochthon layer. This is the flat. This is the decoma surface there. This is you can see that the fold is propagating on this portion. So that is a propagating fold. This is an example of a fold, bend fold. So this is the thrust fold over there. Okay. A nape naman, snape is just like what I mentioned a while ago. It's that allochthonous sheet that has moved along a thrust sequence. In other words, if you haven't eroded, if you don't yet have that clip or that window, it's the whole package that moved for several kilometers because of the thrusting. You call that the whole package as that of the nape. Now, this is not so common in the Philippines. Again, why? Because of our type of rocks. Because the Philippines is a product mainly of oceanic and oceanic. So dense tayo. Continental silica, lighter, so mas madali siyang i-thrust. That's why it's more common to have thrusting and that kind of package in continental areas compared to that of the Philippines. Okay? And how are continents formed, by the way? What is the prerequisite for granite to form? Granite is very silicic, right? Diba? Paano kaya na-form ang continents in the first place? How? Si Kibulo. Si Kibulo. Ginawa na continental. Ano ba yan? What? How do you form continental? Continents, how? We form continents because of the amalgamation, okay, of different island arc systems. So, for example, Philippines is now starting to move northwest, but it will be attached to mainland Asia. So, at some point, mainland Asia is not what Asia that we know. Asia was only formed at the end of the Cretaceous. There is no such thing as Eurasia before the Cretaceous. So Asia consists of various terrains that they now amalgamated, and now because of amalgamation, they form big crust or thick crust. And thick crust is a requirement for the formation of granite. So you do not see granite in the Philippines because Philippines is relatively young. Thin pa lang yung crust natin. Clear. Okay? That's why also continental rocks are very old compared to island arc systems because they are products of millions of years of amalgamation and or accretion. Amalgamation, by the way, and accretion are synonymous in English, but in geology, it's not. You only use the term accretion if one of the component is continental. If we have a continental joining with an island arc, you use the term accretion, terrain accretion. If both are island arc systems or oceanic, you use the term amalgamation. Okay? Terrain amalgamation. Clear? Okay. So more of that. Anyway. So what are the plate tectonic habitats of frost fault? Obviously, convergent margins, right? Example of convergent margins. Manila Trench, accretionary complexes. Have you seen an accretionary complex? Do you know what accretionary complex is? You look at accretionary complex. So this is the subduction there, island arc. Why is it called as an island arc? Why is the Philippines called as an island arc? Because it consists of several volcanoes in a form of an arc. How do we form volcanoes? Lahat ba ng subduction form volcanoes? Ha? Kailan tayo nagpo-form ng bulkan? Ha? May upwelling ng magma. Tama naman. Hindi magkakaroon ng bulkan, wala ka upwelling ng magma. Pero lahat ba ng subduction nagpo-form ng volcano? People, basic question. Hindi. Subduction should reach at least 90 to 100 kilometers for volcanoes to form. That's why if you're gonna look at the East Luzon Trough in Luzon, ba? Wala kang active volcano rito sa eastern part of the Luzon. You have East Luzon Trough there kasi yung subduction niya, jutay pa lang, maliit pa lang siya. Diba? So the distribution of the volcanoes would tell you the angle of subduction. Okay? You get that? Kaya nga alam natin, dito, Batanes group of islands. Tapos the only volcano, active volcano, north of the Luzon, in northern Luzon is what? This volcano over here. Hindi, Iraya nandun sa Batanes. Na mental block tuloy ako. Ano yung volcano din sa Santa Ana to Ligaraw? Basta, papatayin ko sarili ko pag mali ako. I just forgot the name. Okay? But here, diba? Dito yung pinatubo. Tama? That's why the angle of subduction here is shallow, like that. Gentle. Dito, steep. Kasi, dito na reach yung 90 to 100 kilometers, kaya nandito yung bulkan. Zambales, dito ganyan siya. Kaya hindi, sa Manila Trench, hindi equal yan. Parang Negros. Sino taga Negros dito? Kayo, nasa ng Mount Canlaon? Walang sapatusin ko kasi taga-Negros pa. Nandun sa north, di ba? Pating. Nawawala tayo. Pero gusto ko lang sigurado na naintindihan ninyo yung basic kasi ito. Andito yung Mount Canlaon, correct? Pero Cuernos de Negros, nandito siya. Tama. So, anong ibig sabihin nun? Mas matanda si Cuernos de Negros, steep siya. Tapos, nag-change ng subduction, naging gentle. I'm not going to tell you why, but I know why. Hayaan ko din susunod na lecturer. Kaya namatay siya kasi naging shallow yung subduction, nandun siya in 90 to 100 kilometers. Get it? Kung namatay si Cuernos de Negros, nandun ngayon yung porphyry copper natin sa Negros, Southern Negros. Epithermal Negros. Kasi underneath of an old volcano, volcanoes are what? Epithermal systems and hydrothermal. Ilalim niya, porphyry copper. Ibabaw niya, epithermal. May nagtanong nga sa akin, Sir, bakit hindi natin minahin yung vulkan ngayon, active vulkan? Ikaw na. Kasi sumabog yung lava sa mukha mo. Ano tanong yan? Diba? It's crazy. Anyway, okay? So I'm referring to now thrust fault. In accretionary complexes, halika, paborito kita eh. Seafloor, may mga seamount siya, ba? Mga asperities. May mga sediments din siya. Kapag nagsasubduct siya, may mga portions ng subducting plate that are not on ramp but rather are accreted. So when you have this like this, you see how it accretes. Then the thrusting niya is oceanward. See that? Like this. Like that, oceanward. So there are some accreted. So we call that as accretionary complexes. An example of accretionary complex, you go to Western Mindoro, that is an accretionary complex. Mga series of thrust faults na halo-halo yung metamorphic rocks. Kasi you can just imagine, when you form accretionary complexes, there is a very the stress is so great because of the what you call this, because of the collision. Another thing is that sometimes they get partially subduct and then they get thrusted up like this, so they get metamorphosed. So if you go to Antique, you would see also those series of mountains, tall mountains consist of metamorphic rocks. That is an accretionary complexes. Okay? So same thing when you talk about ophelites. Ano ba yung mga ophelites? They were accreted. When you have this distribution of ophelites on the eastern part of the Philippines, it already marks a terrain boundary. It gets on ramp like that. And that's why thrust faults are formed. So if this is dumi-dumi na. Wala ba kayo alcohol? Ito na. Baka mamaya, wag pa, hindi na sumulat eh. Okay, so this is the accretionary complexes, and they are made up of a series of thrust faults. That is what it's directed like oceanward, right? Okay. So this is an example of an accretionary complex in the Philippines, right? So this is the Manila Trench over here. And if you're gonna look at it, at the middle of the South China Sea is this Scarborough Seamount, correct? That is the old spreading center. Now, why is this important? Because on this side, this Scarborough Seamount somehow isolates this from any sediments that are derived from mainland Asia. So mainland Asia erodes continental sediments. And then they get deposited in the South China Sea in this portion. Somehow it's blocked by the Scarborough Seamount, which is this portion over here, this old spreading center of the South China Sea. So since these are a lot of continental derived sediments, when we bring them to the subduction zone, some of them get subducted, but you tend to also accrete a lot of them. That's why you have quite relatively thick accretionary complexes here, unlike when you talk about the southern part of the Philippines. So if you want to see an accretionary complex, you go to Ilocos Norte. Very, very nice accretionary complex there. And the formation or deposits formed within an accretionary complex, which are composed of tectonically complex chaotic bodies, is called a what? Melange. Okay? So if you've been to Palawan, northern Palawan, yung thrusting, Ivanantique thrust of repeated sequences of chert and pelagic limestone, even in Boracay, that is part of an accretionary complex. Okay? Yun yun. Anyway, ba't ba napunta to dito? Yeah. So another portions, okay, so let me just go back to this. So where else do we see thrust faults? Where else? Other than convergent margins. So this is convergent margins. We can also see them in what? In areas near the deformational front or collision complexes. Example of which is the Palawan microcontinental block. So this is the Palawan microcontinental block, and you know its evolution, right? So at some point here, but I already changed this. Robert Hall. Take note, Robert Hall is not, he's very good. Robert Hall. He made that tectonic reconstruction, but he is not the only author. What Robert Hall did was that he got all the models of different authors, he joined them together, including that of Deschamps, and then he came up with this model. Okay? I should know because I'm also a tectonic guy. Ayaw sa akin ni Robert Hall, ayaw ko din sa kanya. Anyway, but you should also credit him for that. Okay? But ang nakakalimutan lang ninyo is that you should also credit most authors. So this model was from Deschamps, Deschamps for other portions. This is my model for the Philippines, iba yung model niya. But for the Philippines seaplate, that is for Deschamps. Okay? But Deschamps already died. Nag-suicide siya eh. Ewan ko bakit. Sayang, no? Anyway, so what I'm saying is that thrust faults can also happen in areas of collision. So if you're gonna look at this, so at some point, this collided with the central part of the Philippines. Correct. But I'm very sure at some point, parang galing kasi, di ba? Gonna look at Palawan. Nung umikot sa Pilipinas, clockwise like this, bakit sa central Philippines lang siya bumangga? Di ba kayo nagtataka? Bakit hindi siya muna bumangga dito sa Luzon bago bumaba dyan? Okay? Pero actually, may evidence ko na bumangga dito at bumangga dyan. Na-publish ko naman siya. Ang point ko lang, this kind of collision is still continuing in the Philippines, right? This collision between the Palawan microcontinental block, okay, of the Eurasian affinity is still continuing here, and the kind of convergence or contraction is accommodated also by these islands over here. You look at the island of Negros, island of Cebu, and for to a certain extent Bohol. They are oriented northeast, southwest, northeast, southwest, northeast, southwest there. And remember in 2013, what kind of fault happened in Negros? Thrust fault. 2013, 2008, something like that. In Bohol, it is also a thrust fault, right? Because of that continued collision. So that thrust fault is accommodating the stress created by that continued collision. So if you do not believe me, you look at that. You look at these islands here also. Island between Cebu and that of Bohol. These are all young coral reefs that are now being uplifted. They are also oriented northeast, southwest. So that's why dito tinitingnan yung Cebu, Negros thrust fault, Bohol thrust fault. Bakit yung Cebu tumalon? But most likely, this is also experiencing that contraction. Kaya ito tinitingnan. Next. Okay? So you see that orientation there? Get it? So it's not surprising why we have that thrust fault movement in the central part of the Philippines. So it's not just along convergent margins, but as well as the near the leading edge of the deformation zone. Clear? So in orogenic belts, I already explained that in continental areas, accretionary complexes, there, yan pala yung drawing eh, pero you see ocean ward like this. Di ba? So if there is a change in the movement from extension, tapos nagkaroon ka ng thrust fault, nag-iba yung movement, then you have what we call inversion. You would notice there's an inversion. Why? Kasi at some point, it is normal fault. Pero pag trinace mo sa baba, pagdating dito, nagiging siyang thrust fault. So, normal thrust. There is, an inversion there. And that part of that fault that move up, you call that as a pop-up there. Okay, let me just stop muna, ha? Oras na. Oh, pwede bang 10 minutes, ha? Ay. are strike slip faults. So strike slip fault is relatively steep dip. Now, by the way, for the thrust fault, we know that the thrust fault is divided into two: a reverse type of fault and a thrust type of fault. A low angle thrust, a low angle reverse fault is a thrust fault, right? A high angle fault is a reverse fault. So when you talk about strike slip faults, oftentimes they have very steep dips, almost sub-horizontal. So at the first order of approximation, when you see an outcrop that it's oriented like this, assuming that there is no tilting, then baka siya ay normal or a strike slip fault. But it's so difficult, really. It's so uncommon to have a thrust fault that is oriented quite steep. And the reason for that is that hanging wall would have difficulty moving up because of the pull of gravity. That's why it's easier for thrust or reverse fault to happen if the angle is gentle like this. Now, for strike slip faults, you know that they are divided into two types. Generally, a pure strike slip fault, right? It can be a left lateral or a sinistral or adextral or sinistral. Kaya pinagsasabi pa ng leftist group sinister, which is not necessarily to evil. Di ba? Pag lefty, kakatakot. Which is not good. No. Leftist, di ba? Left lateral. Okay? So they are counterparts to mid-oceanic faults. So if we're gonna look at the transform fault like this. This is an example of a series of transform faults. You look at the transform fault there. Okay? There are a lot of transform faults. So this is what I'm saying, right? So the Pacific plate is this plate over here. It's very big. Tama. And you see that the Marianas Trench is over here. This is the Philippine Sea plate. It's very, very small compared to the Pacific plate. Kaya ito, ang dali niyang itulak yung Philippine Sea plate because this is very big. Di ba? And also, if we're gonna look at the Marianas Trench is the deepest trench. Why? Why is it deep? Why is the subduction deep? It's the deepest part of the earth. Why? Because of, you look at the spreading center. The spreading center is very, very far. It's here, right? It's very far from the subduction. Remember in the Harry Hess seafloor spreading, as we go away from the center, right? From the spreading center, the rocks get older. Oldest rocks here, youngest rocks there. Oldest rocks, colder. Colder, denser, it's easier to subduct. So that's why if you're gonna look at the distance of travel, it's so far, such that the rocks that are being subducted here are very, very old and cold as well. That's why subduction is steep. Okay, and that is a deep part of the earth. Now, in relation to the strike slip, it says that strike slip fault are continental counterparts of transform fault in the oceanic plate. So if I'm talking about transform fault like this, okay, basic question, what is the movement of this transform fault? Left lateral or right lateral? Left or right? Left. Correct. Left lateral, correct? Tama. Mali kayong lahat. This is a spreading center. Okay? So you look at this. Tama pala, right. Correct, you're right. Ano ba sabi niyo, left? Right, wrong. Guluhan ako. If the reference frame is a fixed reference frame, for example, a road, a house, this would be definitely a left lateral fault. But this is not a fixed frame. It is a spreading center where plates move away from each other. So if they move away from each other, you look at that. This is like this, that is like this. Therefore, that is right lateral. Get that? So the way we determine it for transform fault is different. because that is our spreading center that is being separated by the transform fault. Understood? Again, yung mga nalilito, this is a transform fault, TF. It cuts a spreading center, as you can see from there. Okay? So this moves this way, that moves that way. This moves this way, that moves that way. Correct. So you look at this portion over there, left, right lateral. Okay? Now, second question, why is it that the transform fault ends at some point? Why doesn't continue all the way there? Why? What does it tell you? What? Hmm? Bakit ka tumigil? Because the reason why we have a fault is a fracture, correct? And the way we form a fracture is normally extension. But we can also form a fault if one block moves faster than the other block, even though they are moving in the same direction. Example, this one. This moves this way. That moves that way. If one is faster than the other one, then this would still break. The transform fault ends there because beyond that point, the velocity is the same. You get it? Okay? Tama. Eh? So that is the implication of that. So be very careful when you identify the movement of the fault. Maliwanag. If that is a road, no problem. That is dextral, but it's not. So that's why we're gonna look at it. There are a lot of transform fault, and you see there are a number, several volcanoes there. And as I have said, each fracture there that is separated by a transform fault is a volcano. So strike slip faults are very important because they are the most complex type of fault. It's the most complex because they can accentuate or can form a normal fault as well as a reverse fault. So as demonstrated, if a fault bends, just like what you see there, it can form an extension. Okay? Example, if we're talking about a fault like this, right? So the fault bend like this. And then if the fault movement is left lateral, just like the Philippine fault, like this. So you can see at this portion, the vector is like that. This is like this. There would be a releasing bend there. There would be an extension. So if an extension, what would happen to that extension is that it can form a series of normal faults here. And that can form a pull-apart basin. So you call that as a releasing bend. On the other hand, if it's oriented this way, okay, if it's left lateral, in this case, at the bend, the vectors are like this. It's contraction. So in this case, you have a restraining bend. So in a restraining bend, since that is a contraction, okay, what would form would be a series of thrust faults. So you know the symbol of thrust fault. And you can have even folds like this in between that of the duplex or a imbricate package. So that's why strike slip faults are important to analyze, and they are also responsible for much of the what you call this, the secondary structures like that are associated with this kind of fault there. So here, within that, you can have a negative flower structure. Here, you can have a positive flower structure. So later on, I will show you what a negative flower structure is. Maybe if I can show you it now, a negative flower structure would have some sort of like this. Okay, so this would now be the faults there. So this would now be a series of an echelon, but these are basically normal faults like that. So that can be associated with this is a negative flower structure. Okay, so if we're gonna look at this in a releasing bed, there are a series of normal faults like this. So the dip direction would be like this. On the other side, it would be like that. Clear? Lahat naman ng nakaganyan, it points to the dip direction. That's why the trenches are, the symbol is like this, right? Because that's an area of contraction, compression. Kaya ganyan siya. Pag area of extension, ganun lang. Okay? So this is an example of a negative flower structure. This is an example of a pop-up positive flower structure here. There. Now, it's not just a matter of bending. It's also a matter of an echelon faults. So in an echelon faults, overlapping faults, which I have told you, if we have, okay, let me just ask you, if you have a right stepping dextral fault, would it be associated with a normal fault or a thrust fault? Right stepping dextral. So it is right stepping dextral. So this would be normal. Left stepping dextral. Okay, so this would be thrust. So a thrust here would now be oriented this way. So you can form positive flower structure there. Okay, and then you can also form, maybe you can have a series of pop-up like this, and you can also form a series of fold like this. Understood. So when you are trying to analyze the Philippine fault, okay, so you can even map out all of these lineaments and you will understand why you have a pull-apart basin. Maybe if you go to Surigao, you have a Lake Mainit there. Probably that is also a pull-apart basin. If you go to Northern Luzon, in Cervantes, in Lepanto, there's a pull-apart basin there. And you can analyze it in terms of this one. So, of course, if there will be a negative, okay, an extension, then that is where the sag pad would actually form like this. So then again, another term for that is that if, for San Andreas, sorry for this. Oops. Ay, ano ba yan? Ayoko na. Sumayaw bigla. Nasa na? Anyway, sige. So if a strike slip fault is associated with extension, you call that as a transtensional fault. If it is associated with a reverse fault, then you have a transpressional fault. The Vigan-Ago fault is an example of a transpressional fault there. So you may be wondering why is it that the San Andreas fault is what? Left lateral or right lateral? It's the longest right lateral fault. Because why is it right lateral? Again, you look at the setting. You look at the map of Pacific Ocean there. If you're gonna look at it, the San Andreas fault is a transform fault. This is a spreading center. That is a spreading center there. So this is spreading like this. That is spreading like that. This is spreading like this. This is spreading like that. So as I've drawn a while ago, that's why it's right lateral. Kuha nyo. Right? Understood? So right lateral, hindi left lateral. Naintindihan nyo kung bakit right lateral. So it's different of way. So that's why we expect Los Angeles and San Francisco at some point to be what? Adjacent to one another. Pero patay na kayo nun. So don't worry. Hindi naman tayo taga-America, di ba? Pakialaman ba natin? So the left lateral in the Philippines is the longest left lateral in the world, right? Why is it left lateral? Look again. Pacific plate is like this. Philippine Sea Plate consists of different marginal basins, West Philippine Basin, Paresa-Vela-Shikoku Basin, and then you have some Marianas Trough like this. So this is the spreading center, it's already dead, right? So yan, yung mga parte. So why is it left lateral? Because this plate here, Pacific Plate, is influencing the movement of the Philippine Sea Plate like this. So this is moving like that. This is moving like this. That's why this like this is like that. This is left lateral. Okay? So very clear. How about this? For this fault over here, the Sorong fault. This fault over here, what is its movement? Sorong fault, this one. Left lateral. Bakit? Well, other than this one, left lateral, it's because also, if you're going to look at the history of the Philippine Sea Plate, the Philippine Sea Plate rotated clockwise. So rotation is like this, like that. Okay? So itong dati, nandito siya, nag-rotate pa ganun. So rotation niya pa ganito, therefore it's left lateral. Get it? Okay? So ito, sarado nyo lang yan. Ito, sarado ninyo. Look at this, di ba? You're familiar with this, Marianas Trough. Tapos nakita mo, mahati yan. Yan, intra-arc drifting there. Ito, connect mo dun. Dudugtong siya dun. Ito, dudugtong lahat. Diba? So, a series of arc na nagkahati-hati. Intra-arc drifting there. And then it rotated clockwise. That's why this is right lateral. So, if you really want to look at the very big faults, all you need to do is to look at the movement of these faults there. If, for example, you have Australia moving like this, what would you expect the kind of movement here? Left or right? Baka left lateral mako-form na dito. Diba? Kasi this is moving like this. And if you're gonna look at Australia, this is where they are going to have a problem. There are two types of plates, basic plates. Tama. There are two types of plate. Tama? Oceanic and continental. Correct. Duration plate, is it oceanic or continental? Huh? Oceanic or continental? Hindi. Combined. Oceanic plus continental kasi may pangatlo pa. Look at this. South China Sea is oceanic. So this is a type of plate which is continental with an oceanic leading edge. In the same way, Australia is also a continental plate with an oceanic leading edge there. And that is where the problem is. Why? Because since it's continental, it's having difficulty subducting. Look at this there. So that's why here they are formed as a form of thrust fault, but this is trying to push its way down. Kasi nga, this is oceanic. Kaya ang lalaki ng earthquakes dyan, di ba? So here, the big fault, which that's the 1990 earthquake, July 16, 1919 earthquake. Expressions of the Philippine fault, look at that. The sudden change in topography, a linear base, and there are a series of landslides that are parallel to that lineament over there. And this is also a geomorphological anomaly. Why? You look at this topographic, and this is a ridge that's actually blocking the movement of the river behind it. Okay? Another thing is this. This is an example of a shutter ridge. The ridge are like that, and then you have elongated ridge like this. It shuts the flow of that water, so the river is forced now to bend like this. Okay? Another expression of the Philippine fault. Anyway, that's not that one. Okay? Yan, like this. So, kita mo that, then ito biglang nag-bend. Ang galing ng bahay, nasa gitna. Diba? Malay ba niya? O hindi naman. And more importantly, also, you need to see triangular facets. So, these are expressions of the Philippine fault. So, these are triangular facets. Very nice. Sudden change in topography. Very interesting is this one. What makes this interesting? Because the present is the key to the past. Okay, so this is a fault of the branch of the Philippine fault, may be associated with a transgression because this used to be here, uplifted there. Same thing when you look at this. the present. This is an alluvial fan. You have this. So this is an old alluvial fan. This is the new alluvial fan. So this was uplifted. So this strike slip fault is associated with the thrust component, making it transpressional. Okay? So there are a lot of things I have already taught you about the things that you need to look into. Okay? So what else do we need? Shear sense. Question about strike slip faults. So what are the other tectonic habitats of normal fault? Strike slip fault. How about reverse fault? Strike slip fault. Okay? So all you need to do when you are already practicing geology, first thing, you use remote sensing desktop, try to just trace those lineaments over there. And you would understand, ay, dito malamang extension yan. Siguro may meron ditong pull-apart basing. And pull-apart basing should form what? Obviously, the thinning of the crust. Right? Tama? Now, beneath a fault, especially for strike slip fault, sabi ko nga, they would not just continue all the way. If faults continue all the way, dapat hati na si mundo. The country to the opposite side of the Philippines is what? Ano? Hindi ako sigurado. Brazil yata. Kaya baka pareho tayong Katoliko at mahirap. Hindi ko lang. But anyway, so if the fault moves strike slip like this, then you see the ductile, you see what happened with the shear zone. They just slow, they do not break because the temperature there is already quite high. So that's why the shear zones are important because it tells us also the apparent movement of the fault. If the fault gets eroded, and sometimes it does get eroded, it exposes the shear zone. And oftentimes, shear zones are metamorphic rocks. Oftentimes, because underneath that, the temperature and pressure is relatively high. So that's why, especially for regionally metamorphosed rock, it's interesting to look at some features within it that would tell us the movement of the fault. It can only make sense if you are able to get a piece of rock and that piece of rock is oriented. You get the orientation of the rock before what? Before extracting it from the outcrop itself. So that's why there is so-called shear sense indicators. So there are various types of shear sense indicators including there. But I will just highlight some of this, including those what we call a mantle porphyroclast. We also have some sort of a sigmoidal structure and also the CS structure and so on and so forth. So if we want to look at shear sense indicators in metamorphic rocks, once you get oriented samples, you get a thin section perpendicular to the lineation. Should I say perpendicular to the foliation? So the foliation is this way. Okay, that is the foliation. So you get the sample over there. Get it where you have this lineation. So foliations are this one, the planes. So you get from there. And then you look under the thin section. And you would see myelonitized rock or myelonite. So there are various types of myelonite depending on the matrix. If it's 50 to 90% matrix, that is myelonite. If the proportion is made of matrix is 90 to 100, that is an ultramyelonite. Regardless of what kind of myelonite, there are features there that can tell you the apparent movement of the fault. Okay, so example would be you look at porphyroclasts. Their breaking are inferred to have formed by diminution of grain size. The movement of the fault caused the diminution, lumiit. Okay, lumiit yung mismong yung grain size ng ating moscovite there. So isang titingnan din natin yung porphyroclast, yun man yung lumaki just because of metamorphic growth. So for example, when you look at oblique foliation, right? So if you're looking at a thin section that was drawn from a particular sample there, and the sample is oriented, you can look at the orientation of the quartz. Example of the orientation of the class, they show a particular pattern. If this is the pattern, then the apparent movement is an apparent right lateral fault. Get it? So look at this there, you see this. So the movement is this, that is apparent right lateral fault. Get it? Same way, Ganyan naman usually, no? Tapos you zoom it, kaya isa-isahin mo yung mata mo. There. So that is also an apparent right lateral fault. Of course, it will only make sense if you got the sample in its oriented form. Hindi po pag winasa ko, kinuha mo ganito. Hindi. You need to get the orientation, the strike and dip of that block. Okay? If you are interested. Pero if you're not interested kasi hindi mo ikakayaman yan, ay hiyaan mo na siya. Diba? Lagi kasi tinatanong sa akin yan, if I do tectonic reconstruction, paano ko yayaman niya? Ewan ko sa iyo. Di ba? Sagutin ko ba yan? Mukha kang pera, sige, ikaw na. Anyway, so you can also look at C-type, okay? C or C prime type. So there are C-type shear band consists of S-planes. We have the S-planes there that are cut by a series of cleavages. So you can have a C-type and a C prime type there. So example, what is this? A C-type or a C prime type? Akala ko nalobat ako, naguluhan ako. Buti naisip ko tagal ito nag-CCR ako. So what's that? C-type or C prime type? C-type. Tama. What would be the apparent movement when you have that obliquity? There. Left lateral, right lateral. The S. Look at the S shape there. So that would be left. Ang S niya, fabric. Di ba? Yeah. There. Okay? Anyway, so same thing. We're going to look at the obliquity, maybe in an outcrop. Let me just look at the outcrop there. For CCCS structure, the cleavage there, and then the S type there. So you look at the S type in an outcrop scale, that would give you a sense of movement. That is an apparent left lateral. Okay, so again, this used to be below the surface, erode the top part, the fault, this you expose, the shear zone. So in other contexts, so yun yan, look at that, the S. Kita mo, outcrop scale, bato na to. You look at the S fabric. Tingnan niyo yung mga S fabric. Ito yung mga cleavage niya, there. You see those S there. Right, you can see the S, correct. So there, you see the S? O nagbabulhan lang tayo. Pwede din naman. Kainis naman itong mga to, di ba? It's also an apparent left lateral. So when you have mantled porphyroclast, I explained a mantled porphyroclast. Okay, you can have a sigma, a delta, a phi. So a sigma type, some sort of an S that would also tell you the sense of movement. In a sigma type, you can just imagine this seems to be enveloping the sphere or the circle there. So this is like, and if you have a counterclockwise movement, this goes down like this envelopes it like that. Okay, and this would be a sigma, a delta, sigma, phi. This will be a phi type, which is basically a contraction or compressional type. So when you see this in an outcrop there, right, you're gonna look at this there. So this is a delta type. So the movement would be, if you're gonna rotate this like this, it's enveloping it like this. So the movement is apparent left lateral. So when you see an outcrop, metamorphic rock, baka gusto nyo tingnan ang movement niya. Okay? Because very likely, it can most likely, well, it can represent a shear zone of an old fault system that got eroded. So this one, this is also what? Pangit, no? But no, this is envelopes that way. So malamang ang movement niya, so that's also left lateral. Okay? Same thing. To, pag ganun, umikot to, pag ganyan. Di ba, dali lang pag pinakita kayo ng picture. O, paulit-ulit, parang sirang plaka. Left or right? Right lateral. So, Yes. The fee yan, contraction yan eh. Ito, left or right? Right. Right. You're wrong. Right. Diba? This one there. Okay? This. Okay. Now, take note of bodinage. Bodinage is a product of extension. Diba? You have a competent layer that gets stretched. So, parang nagiging lens siya. So, you can just imagine this used to be just one layer there. This is that competent layer. And because of extension, then you thin this out into a lens and you form what we call a bodinage. Okay. So, that would be an extension. So, any question about shear zones? Okay? So, again, shear zones right now is being used loosely. Basta basag-basag yung bato, sheared. That's yung shear zone. No, that's basically a fault zone. Yes. Laksan mo. So, sinabi sa akin, kung yung fault sa ibabaw ng shear zone ay na-erode, it's na-uplift yung shear zone, pwede mo ma-fault siya? Siyempre, pwede pa naman. Diba? Kung ako yung Philippine fault, talagang tamaan ko yan. Hindi. Kasi because faults can always be reactivated. Diba? And in the same way, remember in the Philippines, we still have a lot of blind faults. Sometimes you expose that shear zone, pero actually meron ka pang blind fault sa ilalim. Faults doesn't necessarily, what? Oftentimes, doon siya sa ilan, tapos siya kayo nag-branch out pataas. Hindi tipong pababa sa siya pinupunta sa pailalim. At some point at the middle of that crust, not just above the what you call this, the shear zone, saka nagta-translate yung mga ganun. No, I have not really read an article na nagsisimula sa surface pababa. I have not seen one. Bakit kaya? Eh, nasa surface na, na-release na yung stress sa surface eh. Di ba? Ano pa? What else? Because this would be the last one, sedimentary. But I'm not going to talk about sedimentary process. It's basically what is the top and what is the bottom. Which one is the top and which one is the bottom. Meron kayo mga sedimentary rocks dyan. Siguro bukas na, no? Pag pinakita ko kayo na bato, which is the top and which is the bottom, you know? Can you give me an example of a sedimentary structure that would tell you which is the top and which is the bottom? Graded bedding. Okay. Eh kung reverse graded bedding. What is reverse graded bedding? Balik nga tayo. Sige, pakita lang natin. No. Ito, Pujada Peninsula. Which is the top and which is the bottom? Ha? Ikaw. Ay, sorry. Tinuro ba naman sama? Ha? Paano mo nalaman? Ang tindi naman na matabo. Hindi na kaagad.
Siya yung steeper na side. Yung sa left side, para yung side na yung sa left. So, side na sa left.
Talaga.
Eroded yung sa left.
Paano mo nalaman? Galing mo naman. Of course, you wouldn't be able to know unless you go get near to it. Di ba? If you are doing mapping, ba't lalapit ka ba doon? Aakit ka ron? Siyempre, you need to look at the sedimentary structure there. Correct. Pero pag nakita mo, oh, pre, oh, ito mismo yung young, ito yung old, galing mo naman, hindi mata mo. I had a student, this is really fun, you know, I had a student, he submitted the report. Ang report niya, from afar, the mountain is weathered. Okay, from afar. Next sentence, it is composed of plagioclase. Sabi ko, wow! From afar, ang tindi ng mata mo. From afar, the mountain is weathered. It is composed of plagioclase. Ang galing, no? Plagioclase talaga, di ba lang nagsimula sa isang porphyritic andesite or what, di ba? So in the same way, you cannot tell. But if you're doing field mapping, saan ka pupunta? Akit ka ba doon? Anong gagawin mo?
Titignan ko lang sa malayo.
Titignan mo sa malayo. Kung meron kang binocular, kung kaya. Ito hindi kaya ng binocular, ang gagawin mo? Ano? Drone. Wow, yaman mo naman. Kainis ko to, no? Hindi. Ang titingnan mo, pag nakatayo ka dyan, right? Tingnan mo doon sa coast kung merong outcrop. Kasi law of lateral continuity, baka meron doon na natirang outcrop sa tabi. Unless there's a fault there. Tama. Or, dito ka lang, malamang may makikita ka na dyan. Di ba? Pero gusto mo pakamatay, magpapakilas yung magkajaywanan kita. Di ba? So of course, you have to be very, very careful because reverse graded bedding can also happen. This is what I'm saying. Normal graded bedding is very good, right? Because if there's a consistency in the finding up sequence that would tell you which is the top and which is the bottom. As I have said, when you have this kind of scenario here in the Philippines, you cannot assume that this is the top and which is the bottom. The principle of the principle of original horizontality, right, or the principle of superposition, of law of superposition, is only applicable in an undeformed beds. It says in an undeformed beds. But the beds, if they are tilted, is no longer applicable. Okay? Because it has been deformed. So be careful also when you talk about succession. This is a finding up succession there. But it doesn't necessarily mean that this is the top and this is the bottom. Not necessarily. What is important is within one bed. There's a difference. Get it? So if you're talking about reverse graded bedding, this might not be a good evidence. You look for other beds. You get it? That maybe may normal beds associated with that. But reverse graded bedding happens. When? When does it happen? When? Low to high energy, correct. In what situation? Ha? Siyempre, pag bumagyo, di lumakas yung ilog mo, tama. Mas madadala siya maraming malalaking sediments. So this is the example here. Okay? Kikita ninyo there, there's definitely a general finding going up there. Correct? Pag dito medyo confused ka rin, parang dito reverse, tapos normal, reverse, normal, reverse. Pero if you're gonna look at the whole section, there's just one bed but it's getting finer there generally. So that would be the top and that would be the bottom. Same thing, this is also in Pujada Peninsula. You won't be able to know there. Hindi mo pwede. So you look at internal sedimentary structures the same way. Example, this one, makikita ba natin? Mahirap. Tama. Reverse normal, reverse normal. So it might be very difficult, but you have to move further, walk further, and look for other outcrops that would tell you which is the top and which is the bottom. But one thing that would be good is the presence of this. Sorry, this one. There. What are these? Ripples. So, ano yung top? Yung top ba ang natira o yung bottom yung natira? Yung top yung natira. So, ito yung bottom. Tama? Oh, yan. Balik tayo. Di ba? Tawag dito? Ripple. Tama? Anong tawag dito sa nagbra-branch? Yan. Bifurcating. Ano ba kayo? Tuturo naman yan si Dr. Garas siguro. No? Yan. So, yan ba yung natira? Tama? Ha? Pwede kaya yan yung natira? O yan yung naiwan? Ha? What you're supposed to do is that it's so difficult to tell. You look at the outer yung gilid niya. Okay? There might be sedimentary structure that would tell you. Kasi pwede naman kasi, na if you're gonna go back here, okay, ito na fill up ng sediments to, ng ibang finer sediments. Example lang, ibang klaseng sediments. You can also have that kind of relationship. No? So what other features that you can look into? Bioturbation. Ang bioturbation nagsisimula sa ibabaw, papunta sa ilalim. Tama? So dapat may dire-diretso siya pababa, titigil siya at sa circle. That can also tell you which is the top and which is the bottom. Okay? So ganyan naman siya. So I'm not gonna discuss that anymore. Alam niyo naman na yan because it is not ang importante sa structural is that you really have to look at these sedimentary structures, di ba? Etc. Yeah. Okay? Ano pa ba kailangan niyo malaman? Sa Bowman sequence also can help you to which is the top and which is the bottom. In a Bowman sequence, you're supposed to see that only in one sequence, one bed. In the Bowman sequence, what is TA? What is the lowermost part? Huh? Okay, that's TA is normal graded bedding. 2B is lower parallel lamination. TC is cross and or convolute lamination. 2D is upper parallel lamination. PE is mud. So basically from TA to PE, there's a general fining sequence and they are products of turbidity currents. So you can also look into that. Okay, that sequence there. So other than that, no, wala lang naman to eh. Kaya ko lang sinasabi dyan, hindi naman to related na sa structure eh. The reason why I just showed you, para sa sedimentology yan eh. You see that this is a Bukaw River, there are a lot of sediments coming out like this. And supposedly they should be prograding out, but it's not prograding out. So when you see this, therefore, baka malamang meron kang submarine canyon dito. So pag submarine canyon ka dyan, doon ka magpo-form ng turbidity currents, right? Ito, this is what you see there, submarine canyon like this, there. So, ang point ko lang dito, pag nakakita ka ng ganyan, huwag kang lalangoy dyan, dire-diretso ka pa ilalim. So, this is the Bowman sequence that I'm talking about. You're just talking about one bed, there's a general finding upward. So, you can look into that. Other features, again, there's an example of this. You see this, normal graded bedding, lower parallel lamination over there. So, this is the cross or convolute lamination, like this. And then the DPD is not evident. So other things that you can actually look into are this one, the flute marks and the tool marks. So the flute mark is a product of what you call this scouring, and the scar is now what you call this fill in by sediments. On the other hand, you can also have a tool mark. There's like a pebble that scarred the underlying surface. So this is also in Puhada Peninsula, which is again one of my favorite areas in the Philippines. So which is the top? The outcrop or yung natanggal do sa outcrop? Yung natanggal yung top or yung bottom? So that is a cast, good cast. So yung bottom ang old or siya yung young? Balik tayo ha. There. So if I put sediments there, okay, sediments there, so that will become a cast. Correct. Now I preserve this in the geologic. Yeah. So this is a flute mark, a flute cast. So yung outcrop, yung papasok ba ng outcrop ang yanging o yung papunta sa atin ang yanging? So, yung papasok yung yanging. Get it? So, here in Mindanao, dito sa area ninyo, actually, have you been to Puhada Peninsula? Punta ka ron, ang dami yung makikita ron if you want to practice structural geology there. And of course, there are trace fossils that I've talked about, right? It forms the tracks, the bioturbation, no? Just like this. So, obviously, ano to? Obviously, yung point ko, which is the top again, going down or going up? Which is the yanging direction? Pataas o pababa ng outcrop? Yanging, ha? It's going up. Diba? Okay? So there are also soft sediment deformation. Example, load casts. So this is a sand, this is a mud. Sand is more dense compared to the mud. So tries to go down like this, the sand goes down, the sand goes down, forcing the mud to go up. So those is, and in some cases, they form some sort of like parang apoy. So you call that as a flame structure. But those are product of basically load structures. So you can make use that as which is the top and which is the bottom. Okay? So in this case, this is an example of that. This is a sand, this is a mud. So this is the top, this is the bottom. Okay? So as I have said, don't just get the strike and dip. You should know first which is the top and which is the bottom. Okay? So look at this. Kahit hindi mo tingnan tong flame structure there, dito pa lang, you would see the graded. This is coarser, that is finer, most likely. Yan ay pag ganun, yanging direction. Consistent. This is coarser, this is finer, yanging direction. So other than that, you have a flame structure there. This is coarser, this is finer. Therefore, this is a load structure, this is the bottom, that is the top. Okay? Then you use your Bronton compass. In relation to your Bronton compass, what time is it? Oh, last. Isang tanong na lang before I let you go. Kasi pagod na rin ako eh. Ano pangalan mo? Parang ang lupot-lupot ng... lupot ka ba? Ano pangalan mo? Ha? Matt? Matt. Ang needle ba ng Bronton compass umiikot or hindi? Ang needle ba ng compass umiikot or hindi? Yes or no? If I open my Bronton compass, this is as a prelude to what will be happening tomorrow, because tomorrow I think would be more analytical. You will be analyzing maps. Okay? But of course, we'll be talking a lot about strike and dip. But of course, a basic question before we go to the strike and dip. If I use my Bronton compass, umiikot ba si needle o hindi? Yes or no? No. Ikaw, yung tingin mo? No. Ikaw? Both. Kayong dalawa. Mag-usap nga kayong dalawa. Nagtitingin kayong dalawa eh. Sige, magkukuhaan na kayong dalawa. Yes or no? Yes. Sa inyo? Yes. Sa inyo? No. Yes or no? The answer is no. Kung umiikot yung needle nyo, malamang sira yung Bronton ninyo. Kakainis naman kayo, di ba? The Earth is a big magnet. So what the needle does is that it tracks the magnetic north and magnetic south. So fixed lang siya doon because it's magnetized. Eh, pag umiikot doon, either sira yung Bronton compass or nababaliw kayo. Dalawa lang naman yan. Or talagang may problema yung mundo. The reason why our magnetic needle, which is the magnetic north, points to the north is because that is actually south. Because opposite poles attract. The magnetic south is adjacent to the geographic north. Tama? Okay? So, para maniwala kayo sa akin, and I hope your Bronton compass is working, you open your Bronton compass, you look at the needle, umikot-ikot-ikot kayo doon. You would see that the needle is just oriented sa north or south. Okay? You use this, right, to track yourself sa map. Tama. Ginagamit nyo to, you use your Bronton compass to locate yourself on the map. Tomorrow, we will be talking about maps. How to analyze structures, which is older, which is younger, what kind of a fault is it, okay? How many geologic events based on the structures that we're talking about. So we will be doing a lot about maps. In the map, Are we using geographic coordinates? Yes or no? Correct. Geographic coordinates, yes or no? Tama. Tama ba? Do you make use of geographic coordinates? Ang reference ba natin magnetic poles or geographic poles? Geographic poles, correct. Ang reference nito, geographic poles or magnetic poles? Then why are we using this? When in fact that the magnetic poles and geographic poles do not coincide. So why are we using this? Why? Remember that the geographic north does not coincide with the magnetic north. They do not. So why are we using the compass? Bakit mo? Paano mo nalaman? Itapong kaya kita sa ano? Dalhin kita sa Britain. Ha? Lagay kita sa Britain. Ha? My point is that before you actually make use of the brought-on compass, you should be able to know the difference between geographic north and magnetic north. Know the angle in your country. To a certain extent, you are correct because in the Philippines, the difference between the two is negligible. In other words, that difference you call that as a declination. The declination in the Philippines is less than 1 degree. That's why we do not change this. We can make use of this. But in other countries, when you do the field mapping, especially at higher latitudes, you need to know the declination correction. That's why you have this screw there. If the declination is 1, then you rotate this. Baka mamaya, oh, I'm already in Britain. Okay, buksan talaga, ganun talaga. Understood? So, paki-familiarize lang tayo sa Broughton Compass. Tomorrow, I will be asking questions about this. Ha? I'm a bit tired already. It's already almost 5:30. Let's just continue the lab tomorrow. And if you have any question, you can continue. But I can entertain questions right now if you have. Even in the Zoom link. Baka nag-alis na sila. Wala? Yes.
Relation ko sa sinabi niyo kanina about group 4 faults ay yung mga mineral districts.
Yeah.
Good afternoon, Prof. My question is, like you mentioned earlier, clues for faults mineral districts. Bakit po yung according sa mga papers na image ng ilang faults at mineral district, yung image ng difficulties like
Mineralization is older. Older. Okay. Okay, that is a very valid question. Remember that if you're going to look at the distribution of mineralization, I am talking about epithermal mineralization here. It's not really within the Philippine fault. It's near to or subsidiary to the Philippine fault. Remember that the Philippine fault only formed recently. But if you're going to look at the Philippines, its present position is not its position before. So before, the stress direction is different. So in other words, you would now start forming these fractures because of that stress. And then you rotate the Philippines like this. Now, it's easy for the Philippines to pass through that or near to it because those are already pre-existing fractures and those are points of weakness. Kung ako yung fault, dadaan ako sa points of weakness. That's the reason why also Philippine fault bends. Kaya siya nagbe-bend because it means a relatively resistant rock. That's why it bends. Okay, so that's why we will see that's not actually within that Philippine fault. It's near to that or subsidiary or secondary to that of the Philippine fault. Okay, so titignan mo yung King, basta from Eastern Mindanao, they are all there near to that, near to the Philippine fault system, but not exactly within that Philippine fault system. Okay? Pero alam natin na dito sa Philippines, marami sa mga epithermal gold deposits natin, they're actually concentrated that along the fault or that. One thing though that is interesting about Mindanao is that wala ako. In Mindanao, diba, sabi ko, yung trench would dictate, or the distribution of volcanoes would be dictated upon by the angle of the trench. And those volcanoes, when they die out, they become source of porphyry at saka epithermal. But here in Mindanao, there are volcanoes at the middle of Mindanao. Mount Apo, Mount Camiguin. Bakit may bulkan doon? And then you have Tampakan. And then you have Masbate Gold District. Actually, your question is very good. Masbate. Diba? Andito si Bicol. The trench, Philippine trench is over there. In Mindanao, it's like this. That red Philippine fault is over there. Volcano, Mount Apo is over here. Camiguin is over there. Ang layo niya sa Philippine trench. If you make a cross-section here, sa Masbate, kung baga ko, dito yung Masbate, the Philippine trench is over there. In the same way, here in Mindanao, the Philippine trench is over there. Cotabato trench is over here. Pero ang bulkan nandito. So it cannot be attributed to that. It cannot be attributed here. Tampakan Gold District is also somewhere in the middle. Tampakan is a porphyry copper, correct? Eh bakit meron kang porphyry copper doon? There has to be an old volcanic system. Why? Ay, balik ko sa iyo. Ibalik ko sa iyo. Bakit kaya? Kasi magulo sa Pilipinas. Bakit? Nawawala na tayo sa topic, but it's somehow tectonics is very related to the structural geology. But let me go back to that question here in Mindanao. Since you are you from Mindanao? And you are from what part of Mindanao? Sige na, ikaw na. Sige. O bakit? Tama. Present model. Mulo Kasiple. Alam nyo, di ba? Scissor type collision. Kung naniniwala kayo, Halma Hera Sangihe. Correct? So, make a cross section. Subduction, create Halmahera arc. Subduction creates Sangihe arc. This is of Eurasian affinity. This is Philippine sea plate affinity. This is a modern day example of an arc-arc collision consuming the Molucca sea plate. So how is it related to Mindanao? How is it related to Mindanao? What is the suture boundary in Mindanao? Where is the boundary? Siayan, Sindangan, suture zone. Central Mindanao and Eastern Mindanao are of the same terrain. Western Mindanao is different. So what they're saying is that it's a extension of that Sangihe collision. In a scissor type of collision, kung nandito yung Pilipinas, magsasarado muna sa Pilipinas. Tama. Tapos dito, pasara pa lang. So what they're saying in Mindanao, sa ilalim daw ng Mindanao, may na floating na slab ng Molucca Sea na na-detach, nag-dehydrate to form this. But we have a problem. That is just a present model. Seismic tomography from the recent, that seismic tomography reported in 2008 does not show any floating slab underneath of Mindanao. Based on the last that I know about the seismic tomography. So what is causing it? Ewan ko sa iyo. Ewan. Kung gusto mag-PhD kayo, I do not know. But for the time being, eto muna tayo. Actually, Mindanao is one of our biggest gap at the Mines and Geosciences Bureau. It is the least map in the Philippines. And yun ang pinakamalaking problema namin because we cannot complete the map of Mindanao, but we need to finish it by 2028. If you can start mapping for free, for the love of science, we would really embrace it. But you have to go to, you have to pass through the technical review committee, syempre, which I am part of. No? Ano pa? Nice question. Any more? So point lang is that the mineralization can deviate away from the Philippine fault. So in Masbate, why do we have in Masbate? It's not because of this, because the trench jumped. If this is Masbate, the trench used to be near to it, then it jumped. Yeah. So wala dito na yung active arc, Bicol arc. You know trench jumping, right? If there's a trench like this, tapos na-develop yung accretionary complexes, so nag-choke yung trench, it would jump. Siyempre, lilipat siya magmamigrate. So, masishift mo yung volcanic complexes mo. Okay? What else? Meron pa? Woo! Grabe. Isang semester structural. Ito talaga ito. Meron? Wala na? So if there are no questions, maybe we'll just continue. Well, we will continue tomorrow, but please bring the things that you actually need. If tomorrow will be more of a practicum, of course, I will be giving a bit of lectures, a series of lectures, and then we're gonna have a set of exercises. If we still have time, then we'll continue with the stereographic projection. But oftentimes, and I think they haven't actually given stereographic projection in the board exam. They have not. But if we still just have time, because the stereographic projection is used for structural analysis and the same time for geotechnical engineering and for also computing the apparent dip. So I hope you know the concept of apparent dip. So tomorrow, we're going to talk about strike line, horizontal beds. How do we analyze it? How do we know which is the younger and which is the older one by just looking at the map that is composed of dipping beds? Okay, so we will also try to analyze the number of geologic events. What is the third event? What is the first event? What is the fifth event? Based on the analysis of the maps. Okay, we will do the 3-point problem, which oftentimes comes out in the board examination. We will also do some basking method so that you will have an idea how the formational units are determined, the thickness of the formational units. I asked one of the students, if you read the literature, for example, if you read the Geology of the Philippines or Lexicon of the Philippines, they also always mention about the thickness of the formation, correct? So how do they measure it? Ang sagot ng dati kong estudyante, sir, i-measure natin, ikaw na. I-measure mo isa-isa yung bed, para kang tanga. Diba? You do not do that. Kailan ka pa matatapos. And one way to solve that is through the basking method. So those would be the emphasis. And also making cross sections. If I show you a cross section, how would you know that cross section is logical? How would you know that it is illogical? Okay? Kuha ninyo. Diba? So bukas yun, and we will start at, okay, sige, maraming salamat.
Thank you so much, Rob, for this afternoon's fruitful and interactive lecture on structural geology. For the program discussion on structural geology, laboratory will continue tomorrow. The same venue is at King Park, 9 a.m. and will also be brought to you live by Zoom. Reminder lang that tomorrow, all the activities are required to bring pencil, erasers, triangle, protractors, and rulers. If you can also bring a stereo net to on angle, content on hardboard, then much better. So thank you so much everyone for coming, and we will see you again tomorrow. Please don't forget to fill out the date attendance. Thank you so much.
Salamat. Ah, hindi ko na nakain. Gusto mo? Ha?